been this morning through to roughly the lunch hour. So our first talk today is by Doug Hiddison. Good morning. So today I'm going to talk about our efforts to put TUV, tropospheric ultraviolet visible radio transfer code inline into music, Wacom, whatever you want to call it. So this is really a status report. We're getting close. We're not 100% there, but we made a lot of progress in the last month. And the people that did all the work are Matt Dawson, Stacy Walters, Kyle Shores. So what I'm going to briefly talk about today is I'll describe TUVX a little bit. I'll show how it fits into the master and not just inline photolysis into our global models. And why do we need to move on from the lookup table approach we've been using for quite a while. And then show some first results just comparing photolysis rates of TUVX inline in CSM2 versus the lookup table. And then talk briefly about our special needs for Wacom. Matt Dawson's probably online, and if you have any like detailed, and system kind of questions about TUVX, you can certainly answer them. But he sent me this slide, and it basically the reason they started with Sasha Madronich's TUV 5.3, and they just basically tore it apart and put it back together. And they brought it up to more modern programming techniques. It's more portable. It builds as a software library, so once it's built, you can link it to any application. It's configurable. There's a lot of stuff, data files or pointed data files was buried into Fortran return routines. They're now pulled out of the JSON files. It should be very maintainable. Should be easy to add in new cross sections, quantum yields by anybody, not just me or Dan or whoever's working on it. And the nice thing about this new approach, as we put it inline, is we'll be able to put the aerosols and clouds in the radio transfer. So we'll have that function we never had in the lookup table. So this is just the example that information has been put in these JSON files. And on the right are cross sections and quantum yields. And so if it's a simple reaction that's a molecule that's already in the database, you could play around with it. You could switch it in or out. If it has complicated temperature dependence or pressure dependence, then you have to go to the source code and work on that. But if you want to just change the quantum yield or something like that, you can do it on runtime. So I think this is going to be really nice for a lot of users going forward. If you want to learn more about TUVX, I asked Matt to put this together. You can go to a GitHub site, and it's listed here, so just download this presentation. You'll have all this information. It runs in a Docker program, and I'll let Dan Marsh talk about that if he wants. So you should be able to run it, download it. Even Rolando can, probably get it going.
Don't count on that.
So go there if you want to know more about how to run the standalone, get a profile of photolysis rates for subcondition. So how does TUVX fit into the grand scheme of things at NCAR? The idea here is we're going to have a cross-section quantum yield database, JPL or whatever source you have. We'll have somebody that manages this, maybe a John Orlando, a Dan Marsh, myself, and other people, just to kind of make sure that what's in there is correct. And maybe give a recommendation on what the best cross-section quantum yields are for any given reaction. But that doesn't mean you can't go out and create your own, and may not go into the database. We have to figure out how we're going to manage this. There'll be something like what Louisa's done nicely with the chemistry cafe. So we're certainly open for comments on this and how to move forward. TUVX, of course, can have multiple radio transfer choices from 2 stream to X stream, 32 stream. Running inline, you got to be careful because it's going to cost a lot of money, computer time to run. Again, the radiative transfer, it is, I don't know if this arrow works. Yeah. The radiative transfer now can have aerosol and clouds, but any constituents. And Chuck has a version of TUV in CSM too, and he's really done a nice job of playing around with this, and I'll mention that later. Sasha Vadronich has something called the web-based quick TUV, and I'll show an example of that. There's the standalone profile that you can run. Music box, so this version of TUV will run the box model, and Louisa talked a little bit about that from the MICM presentation she gave earlier. And then this version of TUV will also support the aircraft campaigns, the CAS and HARP instrument that measures tinting flux. After we get this into TUV, the Harvard group is putting in the FastJ from Prather. I think, doing some comparisons here, because Michael's very good. He's had a lot of experience putting inline photolysis in global models, and we can just make sure what we got going is accurate. This is the TUV web page. It's important to keep this going. Sasha would like that. It's, since 2016, there's been over 231,000 hits on this page, driving photolysis rates. If you look at the HARP CAF airborne and tinting flux measurements, they use this in the field. They take TUV, they measure tinting flux, they put that into TUV, use a given set of cross-section quantum yields, for example, for NO2, and they calculate a J rate. Then they run TUV clear sky without that tinting flux, and that tells them a lot about where they're at, where the clouds are at, if they're flying above the clouds or below the clouds, and that's what this figure on the right is showing here. This is the ratio of the measurements to the clear sky TUV. There are a lot of other things that they do with this model, but that's another reason to keep the database available and the code moving forward so that a lot of people can use it. So global modeling, what are the needs? Well, several people in this room have been working on versions or science topics that require aerosols, sulfate, or soot. Simone has worked in geoengineering, and none of this is, these inputs of sulfate or soot are going into the radiative transfer. So, and that's something I know that she really wants, and it's really important for volcanic eruptions. Susan Solomon works on wildfires, and organic aerosols get into the stratosphere. You'd like to have that affect the radiative component and the photolysis rates. Early atmosphere stuff, Dan Marsh has been working on, where O2 and O3 are low. This would probably be very useful for that. Clouds would be different in early Earth. It'd be nice to know how that's affected. Asteroid impacts, Garcia, Bardeen have destroyed the world several times looking at this topic. They inject soot, water, NOx, halogens, etc. And then the nuclear war scenarios, where again soot, organic aerosols could be injected, NOx will be elevated. And so all these science topics can be addressed if you have a TUVX where the radiative transfer is affected. All right, so this is the first results, and believe me, these look really good compared to the very first results that we were looking at this weekend. And thanks to Matt, he made these plots for me yesterday about 5 o'clock. So on the left is JO2 going to 2O-triple-P, and the kind of goldish line is the lookup table, and the blue line is TUVX. There are some differences here, and these are pretty large differences on the log scale here. So I think we have some issues between the two different versions in the Schumann band and the Hertzberg continuum, but we can track that down. So that'll be fun to look at. It's interesting that ozone photolysis, both branches, I'm only showing one here, right on. So it looks like from the tinting flux on down, the lookup table and TUVX are doing really well. If you go to another species, methyl hydroperoxide, this species has cross sections between 210 and 365 nanometers. It doesn't have any temperature dependence, pressure dependence. I picked this because I just wanted to see what it looks like. And assuming that we're using the same cross sections, which I think we are, there's some differences, but not a lot. So maybe this is some radiative transfer differences. I don't know. But based on this ozone comparison, I doubt that. So I'm a little confused why it's different. Nitrogen dioxide here is another one that's a little different up high. These are the linear scale, so it's not a huge error. But this is probably due to the temperature dependence of nitrogen dioxide, and that's something we can check. So, you know, from my point of view, this is pretty exciting because now we have something that's runnable. We can get into the guts of it. We can start comparing to lookup table, and then eventually maybe Michael Prager's Fast J stuff when he gets that in, or the Harvard group does. There are differences. This was the big one we noticed for bromoform, and I think the lookup table's got it right. It's a more recent update to these cross sections from the NO group. I don't know what's going on in the TUVX, but I can figure that out. Again, these were plots that came on my desk at 5 o'clock last night, so there hasn't been a whole lot of time to dive in.
Is this, are these like just single point with a single amount of cloud, or are they global averages? Or?
So yeah, I'm sorry, I didn't say that. This is the launch. So it's a point in the tropics at 0.47 degrees, and it's a zonal average. And then the bars are the deviation along the zone.
So that could just be clouds causing that shift?
Probably not in the stratosphere, you know. These are run simultaneously, so it should be looking at the same clouds.
But that's the troposphere.
I'm looking at that big drop just below 10.
Yeah, you know what? I
I
think there's a temperature dependence mess up or something there. You know, I just wanted to make a note that this is the kind of stuff we're going to run into, but we can check all these J's out, which will be actually very fun. And then finally, you know, the special needs model, WACM, it's going to have to calculate the heating rates, this from solar energy, the solar energy heating rates, essentially, as we derive the photolysis rates for JO2 and J-ozone. We have to subtract off the bond dissociation energy because all that energy of that photon hitting the molecule in the mesosphere and lower thermosphere isn't realized. Products can go in other places and come back together, react, and release exothermic energy, heat. And
well, we are already doing that, right?
we are, but when you put in the new photolysis routine, we have to rewrite the heating component, and we're going to do maybe a better job than we did before. We kind of just took the photolysis module and then duplicated it. I think we can be smarter on how we do that. Yeah. So, and then we merged. If you guys remember, this is an old figure from CAM-RT that I had, but we merged the photolysis heating rates with the, in our case, will be RRTMG heating rates. And that's how we do it. And so the next steps is really to finish the integration of TUVX and Musica. We're getting close. We'll start testing the sulfate and soots. I'm bringing Chuck in on that if he can help. He's had a lot of experience, and Matt and Stacy have already kind of got a template set up to do that. We're going to start testing the costs of the 4-stream versus the 2-stream and see if we have to minimize wavelengths a little bit in the visible. Hopefully not. I don't really want to go down that fast J path. I'd like to just use the computer power to do the total J. We have to drive the heating rates, as I just said, from a chemical potential heating, and then come up with a cloud fraction approach for the radiative transfer. And there's some options out there, but that's what I got. And so I'm really hopeful by the time the next working group meeting comes, this is going to be done. It'll be, in line in CSM2 or whatever version of the model we have available at that time. Thank you for your attention.
Time for a couple of questions. Dan.
Yeah.
So will you be, the plan though will be to keep the lookup table in there as well as an option? Because what I was thinking is that it would be great if this code could be run for whatever earth you want, and it would then be able to output a lookup table that could be read in. So you could do it right, create a table for a particular atmosphere at, through a shorter run, a year long or whatever it is, get your variability to the table. But then from then on, you could be running 100 years faster.
That's a great idea. Yeah, we could do something like that. Yeah, I was going to redo the lookup table the way we've been doing it, just from the standalone, just to have that as an option for, for some stratospheric or mesospheric studies, you don't really care about aerosol clouds. But for some stuff that Simone's doing or volcanic eruption, you have to care about it. So yeah, well, let's think about that and certainly appreciate your help. Anything else?
Let's move on. We're on a good schedule today. Want to end and have a proper break. So our next speaker is Jin Zhang from NCAR.
Yeah, better stop sharing now.
Okay, so hello everyone, I'm June, and I'm an ASP postdoc working at NCAR. And today I'll be presenting my ongoing study titled Relative Contribution of Anthropogenic and Lighting Nitrogen Sources in the Upper Troposphere during the Asian summer monsoon. This is very preliminary and in progress study, but I think it would be very interesting to share here. First, I would like to acknowledge all my co-authors and for their tremendous help and support. And okay, so why do we want to study NOx in the upper troposphere? So previous study have shown that there is NOx anomaly over the Asian summer monsoon region. I can say that from both the OSIRIS satellite data and the Wacom model simulation. But the source of this NOx anomaly is still unclear. Fidel-Lobis et al. In 2015 found that the transport of emissions to the upper troposphere, lower stratosphere is the largest factor affecting NOx there. But later, Levy et al. Found that lighting is still a key source of NOx in the upper troposphere monsoon region. So the NOx play a critical role in the chemistry in the upper troposphere there. It's a major source for OH production, and it can also affect in PAN formation. And both of them are of importance to chemical species such as ozone and aerosols in the free troposphere. And this would be the first study that thoroughly examine the relative contribution of different sources to NOx in the upper troposphere. So what could be the NOx sources in the upper troposphere within the monsoon region? First, we would have the surface emissions, including anthropogenic, biomass burning, and soil. And among them, anthropogenic is the biggest factor. And also have lightning can produce NOx associated with deep convection. And we also have aircraft NOx emission. Within the stratosphere, nitrous oxide can undergo photolysis, produce NOx, which can also transport into the upper troposphere. Here in my tagging study, we'll be only focused on the tagging the NOx sources from surface anthropogenic and lightning, since there are two major NOx sources, and they are both associated with the monsoon convection directly. Besides tagging different sources, I'm also very interested in the source regions. So I will be tagging the South Asia and East Asia region, shown in the blue and red boxes here. And the region outside of the two boxes are denoted as other regions. By doing this, we can not only know the relative contribution from the sources, but also we know where the sources come from. Okay, how do we tag NOx? In the chemistry mechanism, all the sources are considered simultaneously, but each nitrogen emitted is characterized by an artificial tracer, X-NOx. The example here shows that X-NOx species are added for each reactions related. For species like N2O5, there are 3 pathways that can form tagged N2O5, and they are all added to the mechanism. For detailed mechanism, please look at Lewis's paper. So this mechanism allowed us to follow the evolution of nitrogen from each source and regions without affecting the overall chemical system of the atmosphere, compared to the traditional commonly used technique, perturbing NOx emissions, say like by 20% in a region to determine its impact. This technique can have the advantage of eliminating the non-linearity induced to the chemistry. Okay, so we use the Wacom 6 110 level for the tagging study. It has a horizontal resolution of 1 degree and vertical resolution of 500 in the UDLS region. It also includes interactive tropospheric and stratospheric chemistry. And for all the simulations, I performed it in specified dynamics mode, nudged towards VR2 reanalysis fields from the NASA GEOS 5 data. And I have done 5 simulations in total. The first 2 attacked anthropogenic NOx sources from South Asia and East Asia separately. And the 3 and 4 simulation attacked lightly in South Asia and East Asia separately. And the 5th simulation attacked all the other tropospheric sources that were not included in the previous 4 simulations. So the sum of the 5 simulations should give us the total tropospheric NOx contribution. And we calculated the remaining to be the stratospheric NOx contribution. So before we look at the simulation results, I want to define the regions we look at. So our region of interest are the recent summer monsoon anticyclone and the East Shedding region, because we wanted to be able to compare to the eclipse data later. I will also show the results from background atmosphere in contrast to our region of interest, because it's not directly impacted by the monsoon deep convection. Okay, so let's look at the NOx sources in the monsoon region first. So the pie graph here shows that the NOx sources from 5 simulations and derived stratospheric contributions. And the blues are the contributions from South Asia, with the light color denotes the South Asia anthropogenic, and the darker color is the lightning. Okay, so the orange yellow color shows the contribution from East Asia, with the lighter color from anthropogenic, same as South Asia, and the darker color lightning source. And the gray color here is a contribution from all other tropospheric sources that are not within the 4 sectors before. And then we derive the stratospheric contribution by calculating the remaining, which is 2% here, very small because the monsoon region pumped the surface air into the upper troposphere anticyclone region. Compared to the background atmosphere, where the stratosphere contribute to more than 20%. So in the shedding region here, stratospheric impact is larger than the monsoon region, but still smaller than the background impact. So we can see that within the monsoon region, the South Asia sources, including the anthropogenic and lightning, are the major NOx sources, account for about 60%, while the East Asia sources become more significant in the shedding region, which is 40% more than the contribution from South Asia. Another point is that both the anthropogenic, the lighter colors, and the lightning sources are equally important in the monsoon region. While in the shedding regions, anthropogenic source have larger contribution to the upper tropospheric NOx, more than 20% than lightning. Okay. Now we are looking at NO to OH production in the upper troposphere. So OH production shows a similar results as NOx I showed before. Similar number of percentage and similar functions. So basically, where there's more NOx, there will be more OH production, no matter where the what the source is. Okay, so now we are looking at the PAN formation in the upper troposphere. Compared to the previous results, I showed that anthropogenic and lightning sources are similarly important. The results of the PAN formation is quite different, which I think is very, very interesting. So if you look at the Asian summer monsoon region, the South and East Asia anthropogenic NOx account are the dominant source for PAN formation, which is more than doubling the contribution from lightning. This is also true for the Shetland region. So anthropogenic NOx seem to have higher efficiency in PAN formation than lightning NOx, which I think it could be that the anthropogenic NOx emission are also associated with other emissions of PAN precursors that helps with PAN formation. Okay, summary. So we think the tag mechanism works in the study, at least in this model version. We also implemented the tag mechanism in the 58 level model, which would likely be available in the future too. So if anyone's interested in using the tag mechanism for other studies, I'm not going to repeat the findings here, but I do want to say that for the next step, we want to compare the model results to the ECLIP data, and we want to try to see if we can extract information from the observation data to see where the source of our measured NOx comes from. Okay, thank you for your attention, and I can take any questions.
How much to start with that?
I'm curious if you've tried other choices of domain selection for the background box. The only reason I ask is that during 2022, when we were in the field, we saw some examples of monsoon influence getting out into the Eastern Pacific. So I'm wondering whether you've got, I mean, you certainly have a background compared to the monsoon, but I'm wondering if there's more of a background, I guess. Something like Southern Hemisphere, South Pacific, or something like that, to get, just as an example, to really get into the middle of nowhere outside the monsoon.
Yeah, that's a good point. I didn't test South Pacific, but I did choose different size of the background here because I wanted to keep it in the same latitude.
Okay.
Because then I test the different size of the background, smaller, bigger. It gives similar percentage, maybe like 1 or 2 difference.
Sure.
Yeah.
Okay.
Yeah.
Hi, that was really cool. I was wondering, do you have a rough number how much more computationally expensive is adding all the extra chemistry to the model? Is it like 10% slower? Is the model 50% slower because you have added? I mean, this is cool, right? But I just wonder, for longer simulation, how much more how much time costs? What is the time cost of putting all that together?
So I'm using 110 here. It's already expensive with full chemistry. I'm actually not sure adding tags, how much the computational expense there. I think Louise thought I know. No,
I can't remember offhand, but I think since we're only tagging the NOx, which is a fraction of the species in the mechanism, it's probably on the order of 20%.
Okay.
So it's essentially doubling all the reactions that have nitrogen.
Got a question online from Arlene Fiore wondering if you've also tagged stratospheric NOx to confirm additivity.
No, I didn't, but that would be a good sanity check. I'm not really sure how to tag stratospheric NOx though. Yeah, but
Yeah, because this mechanism tags emission sources, and so
not the production from the nitric oxide.
Yeah, we could do something the way, like we do O3S, that, check if species is in the stratosphere, tag it. But that resets it, stuff goes back and forth when the troposphere in the stratosphere. But that's a good idea. We'll have to think about how to do that.
Beirut, maybe the last question.
Yeah, so about the pan results,
Mhm.
is there any way to separate how much of that pan is coming from, how much of that is formed in the lower troposphere and get transported, and how much of that is formed in the upper troposphere? Is there any way to separate that?
It could be, we could look at the reaction rates information and look at the vertical profile. That probably could give some idea, but yeah, this is definitely, interesting to dig into.
All right,
Okay, thank you.
thanks, Jude. Can we,
You have another?
we can fit one more question in.
Next. So in terms of lighting knots, when I looked at lighting knots in musical or cam, so I found that the uncertainty of lighting knots is about factor 4 from previous studies, and lighting knots in musical is at the lower end. So I just thought if you compare lighting knots in this model to previous studies, maybe lighting knots contribution could be higher.
Yeah, that's a very good point. We only look at the global, lighting knots, it's within 3 to 5 kilogram. But we didn't compare to the location where the lighting produced. That would be good to look at, using satellite data.
You also have ACLIP data where you can look at the knots, and if the lightning knots is too high, you get too much knots, and there is so much.
Right. So we can compare the overall knots, see if they have good representation.
Okay, thanks, June. Thanks, everyone. Let's move on to our next speaker, Ren Smith.
Okay. Trying to, just before I move. Okay, good. All right, I'm almost up there. Oh, I'm still paying attention to the screen up there. There. Okay. Hello, everyone. My name is Ren Smith. I'm a project scientist in the Econ Lab at NCAR. I'm going to be talking about evaluating different configurations of CES and CAM, or the representation of the Asian summer monsoon UTLS. Of course, acknowledge my co-authors, as well as instrument teams from the Stratoclim Airborne Campaign in 2017 for allowing us to use their data to do this evaluation. Let me hide this real quick. Those of you in ACOM or who were at the conversation with Tony B yesterday will not be surprised to see this animation again. This is sort of my de facto starting point every time I talk about the Asian summer monsoon. This is an animation of carbon monoxide from the musical model during summer 2022. So this is the year that we had the ECLIP campaign. And what you're really seeing here is highlighting the importance of the monsoon, Asian summer monsoon convection on the composition of the upper troposphere and lower stratosphere. So you can see individual convective storms that are sort of redistributing boundary layer pollution into the upper troposphere and lower stratosphere. And you see the redistribution of that in the global and sort of the mean prevailing flow at that level, redistributing it to the regions, surrounding regions. And also this can have a pronounced impact on the composition of the lower stratosphere as well. So certainly worth examining. And with that in mind, the 2017 Stratoclim campaign was held in a base of Kathmandu, Nepal, and you can see the flight tracks here and sort of how that fits into the main larger body of the Asian monsoon. This is on the left is just a map plot, and on the right is the vertical distribution. So you can see that the UTLS layer was sampled pretty well there. The gray boxes on the left are model domain choices that I use later on, so I can reference that again if there's any confusion. And there are 3 different configurations of CAM that we use in this evaluation. We have a 110 level WACM that has comparatively coarse horizontal spacing, but comparatively high vertical resolution. And then we have 2 Musica runs. One is a 32 level run with coarse vertical spacing in the UTLS, as well as a 58 level that improves the vertical spacing in the UTLS. This is the this is the Musica grid that was sort of custom developed for our ACLIP purposes. So we use this actually for forecasting, chemical forecasting while we were in the field last summer. And it covers both the region of our sampling in the Western Pacific and also the region of primary convective uplift, as I showed in the previous animation. And then this is a plot that June made, thank you, June, showing the vertical spacing to sort of highlight this, highlight the differences in the vertical spacing. So again, we have the higher horizontal resolution that in the grid, but the Wacom 110 level in orange is the one with the highest vertical resolution throughout the UTLS layer. And although I mentioned that the 58 level has a higher vertical resolution, which is true, it doesn't quite, the enhanced vertical resolution doesn't quite reach maybe as high as we would like into the lower stratosphere here. And so there's perhaps some limitation with that still, but nonetheless, we're trying to analyze different configurations and look for differences. To start out with some map plots here, this is taken from the Wacom simulation, and what we're looking at on the top row are two short-lived species or species with short tropospheric lifetimes, ethane and CO. You can see a very clear and distinct monsoon signature that I should say that these map plots are taken 500 meters above the local tropopause everywhere on the globe. So you can see the role of the Asian monsoon, comparative role of the Asian monsoon in allowing a pathway for these comparative or pretty short-lived species to reach into the lower stratosphere. And the two species in the bottom have essentially indefinite tropospheric lifetimes, CFC12 and N2O. And you can see that the monsoon still shows up as a highlight, but really these maps are essentially just showing all the places that air from the troposphere is rising into the stratosphere because these species are pretty well mixed in the troposphere. So looking at an evaluation in a vertical coordinate space, the top row is in adjusted tropopause relative altitude space, and I should say the grayscale pixels are all of the stratoclimb observations. So we're in tropopause relative altitude space in the top row, and in the bottom row we're in potential temperature space. And then the three models are superimposed on there with the mean lines in solid and the 5th and 95th percentiles as the dashed lines. And I think what's important to mention here is in this type of evaluation, we are actually subsetting the model to the larger stratoclimb region and over the full stratoclimb time period. We're not actually doing an interpolation to the model points. We can do that, but there's still there's an issue with doing that where you have two air masses that you're comparing that have wildly different sizes. Aircraft observation is essentially just a point, whereas a model grid point is something tens of kilometers by tens of kilometers on the side. So we're bypassing that by looking at sort of just the full general behavior of this region. So some nice things that pop out here is that the model configurations do a good job of representing the level of convective detrainment. You can see with my cursor here that there's essentially two modes, one in the upper troposphere and one in the lower troposphere, that you have sort of shallow and deep modes of convective transport. And the models are doing a good job of picking up on those two modes as well as their location or sort of the altitude at which they're detraining. And in the potential temperature space, you can see there's a transition there from convectively dominated to slow diabatic ascent into the stratosphere. And the models are really capturing well the transition, the potential temperature at which that's transitioning. However, the two plots on the right are for ozone, and those are put in a log scale so that you can see the troposphere a little bit better. There is a bit of a high bias in ozone throughout the troposphere and into the lower stratosphere as well. I'm still searching for some good explanation for this, but it does seem like there's just a little bit of a shift. The overall shape is good, but it's a bit of a mystery still at this point. Next, we're looking at some tracer relationships. This is the CO and ozone tracer relationship for the three different model configurations. And what we can see on the left with the Wacom 110 level, that one seems to do the best job of representing the troposphere to stratosphere transition. That'd be the region here in this sort of where CO is decreasing and ozone is starting to increase. The Wacom 110 level tends to do the best job at representing this transition region here compared to the two Musica runs. And our leading theory for that at this moment is that the higher vertical resolution of UTLS prevents this process from being undersampled, as opposed to the Musica simulations that are a little bit coarser in that troposphere stratosphere transition. Next, I'm moving to some tracer relationships. All of these tracer relationships are against CFC12 on the y-axis. So right now we're using a long-lived tracer that is essentially constant in the troposphere to identify sort of how the model chemistry is changing in the stratosphere as you go up. So CFC12 is being used as a vertical coordinate. And on the left side of this, on the left side of these plots here, we have species that have a comparatively short tropospheric lifetime, and on the right side, we have species with comparatively long tropospheric lifetimes. And the ones with longer lived, the ones on the right with longer lived species tend to have, the models tend to do a pretty good job of representing those long-lived tracer relationships in terms of how that's transitioning into the stratosphere. The ones in the shorter-lived leave a little bit to be desired. I have started doing this in my meetings with Laura, where I essentially are using emojis to characterize this, but you can see this is basically saying in emoji form what I've been saying here. The ones on the left are leaving a little bit to be desired. I'm going to touch on that a little bit more in a moment. We want to, rather than just waving our hands and saying, you know, we see these ones look like they're doing better and these ones look like they're doing worse, we want to actually provide a way to score these and give some kind of a quantitative metric for how well they're doing how well the models are doing against observations. So with that in mind, I won't sit and dive too much into the specifics here, but we've defined a quantity here called the mean absolute percent error, essentially quantifying the spread between the observations and the models on those tracer relationships before. And if I put all of these scores together and look at them in a more sort of collected sense, you can see the same thing that we saw on the last plot, where the shorter lived, and these are organized in terms of lifetime here, but shorter on the left still and longer on the right still. You can see that the ones on the right side are doing a pretty good job against observations. And again, we qualitatively saw that on the last slide. But there's some question as to what's going on with these shorter lived species and why these ones are or why the models are struggling with these a little bit. So one of the things that we looked at, these are two species, methyl bromide and methyl chloride, that perform particularly poorly or seem to perform particularly poorly in their representation. And what we've sort of elucidated here is that these, a lot of the species that we've looked at for the Stratochrome data are all simulated in the model using a zonally averaged mole fraction boundary condition. For the longer lived species, as we just saw, that doesn't seem to lead to any problems because of their long tropospheric lifetimes. However, for some of these shorter lived species, these two examples, as an example, do not show really a monsoon signature. The observations over the monsoon are in black. The models are really missing that. And so what we did to try to highlight this as the culprit, this zonal average mole fraction boundary condition, is plot in gray some observations that were taken from 2013 Seekers campaign, which was taken over the Conus region. And those line up really well with the model. And that really kind of gives us a smoking gun here for the fact that there's a monsoon signature here that's being smeared out in this zonally averaged sort of boundary condition. And, you know, again, the zonally average condition is okay for those longer lived species, but for these shorter lived species, tends to lead to some errors in terms of the representation. Okay, so let me move on here. So I think the big picture idea that we're going for here is to try to establish these kinds of diagnostics for a process-based model evaluation. So we've used this these airborne chemical observations, a tropopause relative coordinate, and these tracer relationships as a way to analyze and evaluate these models. The key here is that we're using these to bypass the size disparities between a large model grid cell and the comparatively small airborne observation point as well. And using these diagnostics that we've developed, we get these sort of conclusions that this is the same stuff that I've already said. The models are generally doing a pretty good job of representing Asian summer monsoon chemistry and dynamics. There's a bit of a high bias in ozone, and there's some issue with the representation of shorter lived species when they're represented by the zonally averaged mole fraction boundary condition as well. Again, overall, I think this is, you know, a lot of the things that we've looked at are very good news for the representation of the Asian monsoon. And it's really highlights that we believe that high vertical resolution as well as high horizontal resolution are both important and have tangible benefits for the representation of this kind of process. And my very last slide is more or less saying the same thing that Jim said, is that we're very interested in applying this to the 2022 ACLIP mission, which just took place from Korea last summer. And these two maps are showing sampling from the G5 aircraft and the NASA WP-57 aircraft, as well as the vertical sampling on the right side. These data are not final yet, so we weren't able to include them in our analysis for this meeting, but nonetheless will give us more of a window into the monitoring processes. So, thanks for your attention. Take any questions. Yeah.
The tracer plots that you showed,
Mhm.
it seemed to me that you said Wacom was doing well, but then I was curious why the higher vertical resolution seemed to make things worse in the two high-res runs. Is that right? The spread is wider on the right than the left, than the center?
You're saying that the spread is wider here in these
No,
musical units?
58 versus 32. It seems that if you're looking for a nice compact distribution, it seems like it's almost wider in 58 than 32.
Yeah, I would say it seems to be a little bit wider. I think there's more model points that are available in that run just because of the higher vertical resolution. That's probably why we end up with a bigger spread. So there's more model points. So part of the one thing I can do to improve this a little bit is to say if we have a very small amount of points, only 1 or 2 points, we can drop that off of the distribution here. So that will actually show up in here, but it's probably a little bit misleading to put that there. So, yeah.
So the ozone's high, and some of those species, short-lived species, have fast reactions with OH. So it seems like if the NOx is not quite right coming up either the surface or the lightning, I think pushing both ozone high and destroying the short-lived. I guess June's probably looked at that with some data, but not this data.
Mm-hmm. Yeah. I haven't looked at NOx, and I think we should have the stratiform data. That would be a good thing to look at. Yeah. We're still.
I don't know how the lightning's been tuned for that part of the simulation.
Yeah, I know you have played with the lightning settings in different simulations, and I think that these ones are all untampered with in terms of that, but it'd be good to make certain, I guess, and be interested to look at that.
One more question? Not. Thanks, Brent.
Thanks, everyone.
Let's move on to our next speaker, who's Xinyue Wang. She here? Michelle Wang.
She's
Oh, she's here. Okay. Thanks everyone for sticking on schedule. I appreciate that a lot.
Good morning, everyone. So today I'll be talking about the stratospheric climate anomalies and ozone loss caused by this Tonga volcanic eruption. So a little bit of background here. So just like any other large volcanic eruption, this Tonga injected about 0.4 teragram of SO2 into the stratosphere, which then quickly converted to softly aerosol. So if you look at this observation showing you the stratospheric aerosol text, you see that this Tonga induced more aerosol than any other volcanoes or wildfire events in the last 2 decades. But what makes Tonga so exceptional is this large amount of water vapor that got into the stratosphere at this time. So if you look at this panel below showing you the observation of the total stratosphere water vapor burden, you can see that the Tonga has induced an increase of overall 10% in the stratospheric water vapor. That is something we've never seen before in the satellite era here. So therefore, it's important for us to understand this large perturbation in the atmospheric composition. How does it change the temperature and the circulation in the stratosphere? And how does it change the stratosphere ozone chemistry? And in order to understand these 2 questions, we need to make use of our chemistry climate model. So the model we used here is this whole atmosphere community climate model, WACOM, developed by ACOM. So in total, we have 3 experiments. So 1 control case and 1 SO2 only case with only the sulfate aerosol influence, and 1 SO2 plus water case with both SO2 and water injection, which mimics a total forcing due to Tonga. And also for each experiment, we have 10 samples just for statistics. And you can find more details in our paper here. So here, I just want to show you this involving volcanic plumes in the observation first. So you know that this volcano erupted in January 2022, so two months after the eruption. You see that on the left, I'm showing you the observation in March, and you see this sulfate aerosol plume as in red contour here, and the water vapor plume as in red color shading here were co-located in the stratosphere near 20 hectopascal. But in August, you see in the middle panel here, you see this sulfate aerosol has descended to the lower stratosphere and mixed into the polar region. Meanwhile, this water vapor plume was still centered around the 20 hectopascal, and you can see that it was excluded from the polar vortex. And then now is our model simulation for the volcanic plumes for the same months. And you can see that overall our model can capture this involving volcanic plumes quite well. And also we know that this water vapor plume has radiated force in the stratosphere. It tends to cool the stratosphere. But the sulfate aerosol plume is going to warm up the surrounding air. So how do this combined effects is going to change the temperature in the stratosphere? So let's see what happens in the observation first. So on the left right here, you're looking at the spaghetti plot of temperature in the stratosphere in the satellite. So gray contour shows you the temperature for different year, black is the climatology, and the red is the data of temperature for 2022. And you see that it's very obvious that following the Hunga-Tonga volcanic eruption, we have a big cooling anomaly, and it's outside of all the internal variabilities. And then now I want to show you where this cold anomaly happened as a function of time versus height. And you can see that this cooling anomaly in 2022 mainly occurred in the middle stratosphere. And you see that it got stronger with time and then maximized in the winter season in the southern hemisphere, but slowly come back to normal afterward. And then now, again, it's our model simulation. And then you see that overall, our model can capture this cooling temperature anomaly with surprising details in this total forcing round with both water and SO2 injection, which demonstrate that this temperature anomaly we see here in the observation is a fingerprint of a response due to this volcanic influence. And also our model sensitivity experiment tells us we need to include both water and sulfate aerosol in order to capture this temperature anomaly in the similar model simulation. And in addition to this large temperature cooling anomaly we see in the stratosphere, we also see a big change in the circulation in the stratosphere following the Hunga-Tonga volcanic eruption. So on the left, you are looking at the observation of zonal mean zonal wind in observation. So gray contour tells you where the climatology of polar vortex is, and the color shows you how it has changed. And you can tell that there is an equator shift of the winter polar vortex, and which is in balance with the cooling anomaly you see in the one slide earlier. And then now is our now is our model simulation. You can see that again, our model show a good agreement with that to the observation. And the vectors you see there are anomalies in Brewer-Dobson circulation. So you see this ascending motion in the higher latitude, but descending in the tropics region, which is the opposite of the normal background. So here it suggests that there's a weakening of the Brewer-Dobson circulation following the Hunga-Tonga volcanic eruption. And as a result of this slowing down of Brewer-Dobson circulation, we see there's a change in the ozone anomaly in the same month. So as you can see from the left plot here showing you the ozone anomaly in August. You see that there in the mid latitude, there is a large ozone reduction there, as this blue block shows you here. And on the right, I'm showing you again spaghetti plot of this ozone mixing ratio around the same height. And again, black is the climatology, red is the ozone mixing ratio for 2022. You see that this ozone reduction again is something we've never seen before. And also our model can reproduce this ozone anomaly quite well. And we did an ozone budget analysis. We found that this ozone reduction in the mid latitude is mainly due to the change in the circulation rather than the chemistry process. Okay, so in addition to this big ozone reduction in the mid latitude, we also ended up with a large ozone hole last year. So right here, you are looking at the ozone anomaly in the spring seasons. On the left, you see that there's a big ozone loss associated with Antarctica ozone hole there. And on the right, I'm showing you this spherical ozone burden over the Antarctica region. Again, black is the climatology, red is the data for 2022. You see that there is a loss about 15 Dobson unit following this Tonga volcanic eruption. And now I want to show you our model simulation for this stratospheric ozone burden. And the black is our control simulation, and the red is the total forcing run with both SO2 and water impact. And the blue is the SO2 only run. And then you can see if you compare to the control run, you see that the combined impact due to water and SO2 has led to a net ozone loss around the 15 Dobson unit, which again works well with that happening in the observation. But if you look at this blue curve here, you see that the SO2 only run has a similar ozone loss, so which suggests that this bigger ozone hole last year is mainly due to the soft errors of the chemistry process rather than dynamics change, the temperature change. So a quick summary here, following the Tonga volcanic eruption, we see a persistent stratospheric cooling, equator shape of the polar vortex, and a slowing down of blue bubble circulation. So these three are all in balance with each other. And in terms of the ozone change, we see there is a big ozone reduction in the mid-latitude. That's mainly due to the dynamics. But we also see a bigger ozone hole last year, and that's mainly due to the sulfur aerosol following the Tonga volcanic eruption. And what's more important is that our model can capture the symbolic plumes quite well, and we can reproduce this observed anomaly also quite well, which suggests that this anomaly we see there are fingerprint of response due to the volcanic influence. And thank you for your attention, and happy to take your questions.
There are plenty of times for questions. Let's go around.
So the high water vapor, it has a long atmospheric lifetime. So in 2023, in the southern hemisphere vortex, it'll be interesting to see how that affects PSCs.
I don't have the simulation here, but I agree with you that the weather plume is going to stay in the stratosphere for a long time. And when the vortex breaks in this coming season, I think the water vapor will eventually mix into the Antarctic region and have impact on the polar stratosphere cloud and therefore impact the ozone chemistry.
Have you run the interactive model at all forward?
I'm working on that.
Okay.
Right now, we only have 5 ensembles, whether we want to make it 10 to have a robust changes.
David?
Have you, for your last part, when you diagnosed the ozone loss in the Antarctic spring, have you done it from the free running simulations or the specified dynamics?
This all free running.
So I was wondering, because polar vortex in Wakam is presumably too strong in spring and therefore it's too cold. So you get just the right ozone loss. but if the temperatures in the vortex are presumably too cold, does that suggest that you are underestimating, overestimating ozone loss? Do you know what I mean? Because like
Yeah.
your ozone loss on sulfate is going to be a function of temperature, and presumably the temperature is too cold in the climatologically cold,
Right.
right? Do you have some
Right.
sort of
Yeah.
what the ozone loss would be if we Wacom was have a fully realistic climatology?
Where we have validated our model simulation against the observation in terms of the temperature. So if you look at here, you see, we have the, oops, 3. You can see that if you look at the observation of temperature in October, you see that it's cooling about 10 minus 10. But if you go to our model simulation, you can see that actually we have a warmer bias
Okay,
that which suggests that we may underestimate the
Okay.
loss.
awesome, thank you.
Yeah, Valerie?
You're probably aware that NASA Weather Space Flight Center is basically last year released screen chemical analysis for stratospheric species using MLS data. And there are a couple of papers already published with diagnostics of risk analysis for whistle events, and I would say you can download the screen data and basically make verification. The screen data is full chemistry evolution from 2004 until now, and basically all chemical species observed by MLS, and it's on the mirror grid exactly half degree evolution, 72 days. If you want, you can basically get more credit results just comparing with chemical data simulation study versus your pre-running model.
Okay, thank you for the information.
I'm just suggesting.
One more question? Dan?
You showed a mesospheric warming about the stratospheric cooling. Is that
Right.
also a Brewer-Dobson circulation
Yeah,
response?
that's in balance with the changing stuff.
Okay.
All right. Thanks. We will now move on to our final speaker, Eva Bednarz, who's going to talk about gravity wave optimization.
Effective.
I think we interested to extend this to this summer of 2027. Discussion, I think it should have an impact on PM6.
Okay, so hi everyone, I'm Eva, I'm a research scientist in Series and NOAA down the hill. So I'm going to be talking about how the stratospheric aerosol injection and how the uncertainty in gravity wave parameterization in CSN2 in particular affect the simulated climate response. And just a disclaimer, this is still very much work in progress, so but I hope it's going to be still interesting. So I'm sure most of you have came across about stratospheric aerosol injection, but just to make sure everyone is on the same page. So stratospheric aerosol injection is a proposed geoengineering method that basically aims to temporarily offset some of the negative impacts of climate change. And the idea relies on the injection of sulfate aerosol precursors into the stratosphere. So in particular, we are talking about the SO2 gas, which is then gonna oxidize in the stratosphere into sulfuric acid, and sulfuric acid in turn is gonna nucleate into aerosols or coagulate on pre-existing particles, forming a layer of sulfate aerosols in the lower stratosphere. And then once in the stratosphere, this layer of aerosol is gonna reflect a portion of the incoming solar radiation, thereby reducing surface temperature. Let me just hide that. Okay, so let me just point out that there are many uncertainties to such an approach. First of all, there are all the microphysical uncertainties associated with the efficiency of SO2 to aerosol conversion, and then eventually its later removal out of the atmosphere. Then there are all the dynamical uncertainties associated with the transport of the aerosols from the rejection region, usually in the tropics, to mid and high latitude by the circulation and mixing. And there are also uncertainties in basically how much cooling you are get for a given amount of aerosols in the stratosphere.
And there are uncertainties in many of the indirect and indirect impacts of SAI, for instance, on atmospheric circulation and clouds. So what I'm going to focus today is the second uncertainty associated with the transport of aerosols. I do want to put out that this is just, even though I'm highlighting this bit, this uncertainty is going to ultimately affect all the other uncertainties as these processes are ultimately connected. So first, I'm going to talk about two different parts of gravity wave parameterization. First, I'm going to start with convective gravity wave drag. So in the standard workhorse CSM2, WACAM6, L70 model, so the 70-layer model, the convective gravity wave drag is basically what drives the quasi-biennial oscillation in the model. And in this particular parameterization, the wave phase speed is related to the depth of convective heating region, the maximum convective heating, as well as the zonal winds in the heating region. And as a sort of side effect of this sort of parameterization of such an approach, the QBO speeds up in a warming climate as surface temperature increases, there's more convection, and therefore the amplitude of the gravity wave increases. So here is the simulated equatorial zonal wind on the top in the WACAM6 1-degree version, and at the bottom is ERA 5. So you notice that the model, this model version has 2-week amplitude of the QBO, especially in the lowest stratosphere, where there's basically no QBO. And then what you might not immediately notice from just eyeballing the plot, but also the period of the QBO is a bit too short compared to reanalysis. So what we've done, we've tweaked the parameterization to somehow uncouple the convective gravity wave drag from the convective heating region in what we call the gravity wave fixed setup. And in particular, we prescribe climatological heating area, heating depth, and maximum heating amplitude. And as a result, we get a larger amplitude of QBO and a longer period of QBO. And also we prevent the QBO from speeding as much as in the standard WACAM version. There's still a little bit of speeding up, but it's smaller than it was in the standard CSM2 version. So this is just the amplitude of the QBO in the standard version in red, and the amplitude in our perturbed gravity wave drag parameterization. You do notice the amplitude is stronger, but it's mainly still above 30 hectopascals. So we didn't manage to actually make the QBO stronger in the lowest stratosphere. So in terms of assessing how much impact does it have on the uncertainty associated with the stratospheric aerosol injection, we performed a set of simple SAI simulations with constant SO2 injections in the lowest stratosphere at the rate of 12 teragram SO2 per year. And because this QBO is strongest, the modulation of the QBO is stronger at around 30 hectopascal and above. We've done those simulations with the injections at 2 different altitudes, first at 22 kilometer, which is similar to what has been done recently in the recent CSM2 engineering simulations called the RISE SAI. And then we've also done a simulations where we inject at slightly higher altitude, so 30 hectopascal, which is similar to the older engineering simulations with CSM1 called LENS. Okay, so these are the simulated changes in aerosol optical depths in the 4 simulations. First, as shown in the black line, the turbine QBO has little impact on aerosol optical depths for injections at 22 kilometer. In this model version, this is basically, we don't really have QBO at this level. However, as we move to 25 kilometer injection, the new parameterization leads to higher aerosol optical depths at the equator, and then slower aerosol optical depths in the northern hemisphere. So we are talking changes in the order of 10% or so, which is not huge, but at the same potentially important. And then in terms of impacts on the associated temperature response at the surface, so in the northern hemisphere, because of the interannual variability, we only see an impact in the subtropics, so we get slightly warmer, slightly less cooling under the new parameterization, but no significant changes over the rest of the northern hemisphere. And interestingly, even though the AOD didn't really change that much in the southern hemisphere, we do see a significant reduction in temperature response, a significant increase in temperature response at the surface of more cooling at both 22 kilometer injection and 25 kilometer injection. And we're still working on diagnosing where it's coming from, but the results suggest this is due to, at least partially due to slightly stronger climatological polar vortex in the southern hemisphere. And again, we are diagnosing where it is coming from, whether it's due to the intrinsic QBO teleconnections with the high latitudes, or whether it's due to different gravity wave flags outside of the tropics. And also we're exploring whether there's any coupling once you put stratospheric aerosol on top of that. So now how am I doing? I'm doing fine. So now in terms of the impacts associated from the orographic gravity wave drag parameterization. So as you probably know, the orographic gravity wave drag is primarily important in in modulating extratropical stratospheric circulation. So we're talking winds and Brewer-Dobson circulation. So in CSM2, there's now a new parameterization that has been an improvement from the one in CSM1. And without going into details, there's a number of tunable parameters in this new parameterization that basically control the scheme's efficiency. And the default value for those parameters is 1. And here I'm going to vary them between 0.1 and 3.0 to illustrate the impact this can have on the polar vortex. So this is the polar vortex in this workhorse CSM2 WACAM 6 1 degree version in black. And the ERA 5 is showing purple. This is zonal wind at 50 hectopascal yearly mean. So you notice that the polar vortex is too strong in the southern hemisphere in the model. And then in the yearly mean, it doesn't look too bad in the northern hemisphere. However, do believe me when I say, like, if you look at just the northern hemisphere winter, DJF, the polar vortex in the northern hemisphere is too weak compared to ERA 5 reanalysis. So there's this opposite sign bias on both hemispheres, on the different hemispheres. So what we can do, we can modify the gravity wave efficiency, so we can reduce the amount of orographic gravity wave drag to make the polar vortex stronger. And again, we are affecting this both hemispheres, both polar vortices in the same sense. So we are strengthening all of them, both of them. And we can also increase the gravity wave drag, and therefore this is going to weaken the polar vortices in the two hemispheres. So I'm going to focus on the two endpoint cases corresponding to the cases with high gravity wave drag and low gravity wave drag. So on the right hand side, so on the left is the zonal wind again at 50 hectopascal. On the right is the corresponding changes in the meridional component of residual circulation. So in red, we've got the case with low orographic gravity wave drag and therefore stronger polar vortices. And this corresponds to weaken to decelerated shallow branch of the Brewer-Dobson circulation. And in blue, we've got the case with high orographic gravity wave drag and weaker polar vortices and stronger Brewer-Dobson circulation in the lowest stratosphere. Okay, so assess the impact this can have on the simulated SAR response. I'm going to carry similar single point SO2 injection simulations in the lowest stratosphere. And this time I'm going to impose SO2, well, inject SO2 at either 30 degrees north or 30 degrees south. And here are some preliminary results with only 10 years of simulations. And I'm focusing on the spring in each of the hemisphere because the differences are largest the differences are largest in winter and spring when the cumulative impacts of transport processes on aerosols is largest. So in this case, we find changes in simulated aerosol optical depths of around 10%, maybe 20 if you are, depending how you take the differences, which is again not huge, but potentially important. And so this is still the preliminary results in terms of where we're thinking of going. We do want to assess the sensitivity for injection of SO2 closer to the tropical pipes. So in this case, we're talking about the 50 north and 50 south injection, as is commonly used in CSM during GEA simulations. And so far, as I've said, we only have 10 years of data, and we do ultimately want longer simulations to assess the impacts on surface temperature response. And I'm also interested in looking at the impacts the uncertainty in stratospheric circulation has on the simulated stratospheric ozone response. And this in terms of the how much heterogeneous ozone depletion you get in the high latitudes, and how much ozone transport you get also to the high latitudes, especially in the northern hemisphere. And then eventually, I'm also interested in looking at the impacts on high latitude dynamical response and how much uncertainty on that can become from the model dynamical fields. And with that, I want to thank you for your attention, and please stay tuned for future updates.
You gotta have a question.
Well, I was trying to wonder what, I mean, this is just a sensitivity study.
Yeah.
You're not proposing that we should adjust
No,
efficiency.
no, no, I'm just sensitivity because the models have
Yeah.
climatological fields that are
Yeah,
all over the place.
Yeah,
So I just wanted to see, take the perturb only climatological
Yeah.
transport in one model and see how
what
much.
happens when you do these things? Because of course, one thing that happens with the jets is that if you increase efficiency, you slow down the jets everywhere. So I mean, you cannot fix both the northern.
Yeah, no,
hemisphere-
I'm not proposing this is
Right.
what we should be doing. I'm just trying to explore what is the impact
What is
of
the
the model climatological fields on SAI response.
Right. Yeah, I think what WACM is missing in the southern hemisphere is the lack of propagation in the meridional direction. Especially for the orographic gravity waves. I mean, don't have lateral propagation because everything is in column physics. And so that's an important effect that is missing. And there's really no way to fix it, you know,
Yes,
unless you go to a different way of doing gravity wave forcing. Yeah.
Yeah, I was talking to Julia, he also thinks that.
I mean, Julio has told me he has some ideas, but and he never went anywhere. Yeah.
It seems like a very hard problem.
Yeah.
Pointed out the northern hemisphere has a bias.
Slight bias.
Right, and but you're looking at DJF. I was wondering if you actually, that bias is not constant through the winter, right? It's high and low and then high in terms of the wind biases. And I was just wondering if you actually saw a better seasonality as you played around with the settings on the gravity waves.
I mean, I looked at it a bit, but you're basically messing up the polar vortex throughout the seasonality, I think. So it's like, if in the original parameters, if original setup, you get the wrong DJF vortex, like a true weak polar vortex, then we might still be having a realistic representation of polar vortex in spring or autumn. So if you just perturb the gravity wave drag, it's gonna make the DJF better, but for instance.
Now I'm talking about within DJF, so it's not, the biases are not constant. It's not like it just shifted down. It's actually lowered and then gets stronger later. And so I'm just wondering whether that seasonality over the winter,
Okay.
the bias actually changed as you played around with the gravity waves. It might be interesting just to look at the daily data.
Okay.
And then just see
If that's okay.
what it's doing.
That's a good solution. Thanks.
Yeah.
Actually, is it orographic gravity schemes what we have McFarlane or it's Julia scheme?
What? Sorry, I didn't get it.
It's
Julio. It's the rigid screen.
Oh, this is the new rich parameterization based on Sinoka's work.
Yeah, with some further updates, apparently.
But then it had a bug recently, but now.
In topography, not in the scheme.
Yeah.
And not in these runs, which
Right.
make me really happy.
Well, that's just your special.
Yeah.
So I kind of missed the point with the QBO. You were tuning the QBO and the 70 level differently. Is that what you were saying?
Well, no, we're tuning the whole of QBO, but the point being that most of the for most of the SAI simulations are currently done with injections lower down, because like if someone was ever to think about it seriously, it's really hard to imagine flying to 25 kilometers. And also like the air results start evaporating at some level as you go too high. So now most of the SAI simulations are done with injection like 20, 22 kilometer. But when we've done it for injection at 22 kilometer, basically there's still no QBO because it's a 70 layer version. So there is not much QBO there hasn't been much impact on the QBO at 50 hectopascal. So that's why we've done some like a sensitivity test when we injected at 25 kilometer.
Yeah. You cannot fix the QBO below 50.
Oh yeah, no, I
hectopascal.
absolutely know that we need to use the 110 version to get the QBO, but
Yeah,
I just stick
you need higher,
to 70 because this is what most of the geoengineering simulations are done.
Right.
So yeah, I do fully acknowledge that we need 110 layer version to look at QBO.
Is it quick?
Or the 93 level version that is coming up, if 80 kilometers is sufficient for the car.
The CAM.
No, the workhorse coming 80 kilometer top.
But is that WACAM or is that CAM?
That's
Well, we call
Warhorse.
it.
I don't know, I'm still confused what are the differences, but like, yeah, 80 kilometer would be absolutely fine. That's what like, on lots of models, climate models, they cap at 85 kilometer.
We do this offline. maybe.
2 minutes.
Yeah.
Cam X Wacom. That's what we're calling. I don't see any questions online. Thank you. That was great. Yeah, Dan is letting me know we are 2 minutes over into the break.
Which is
You
amazing.
can blame me.
We all, anyway, we'll come back here at 10:35. I think coffee's by the main seminar room for more talk.
You gotta get over there before those.
Thanks, everyone.
Oh,
Oh.
I do always that. It's just, yeah, I apologize. No, it's just like something I've been
I
doing.
have a quick question for you.
Yeah.
So in the graduate fix, what exactly do you do? You fix the heating?
So currently the default version is basically, the model looks where the convection happens.
Right.
Then when the heating depth is above some threshold level, it basically says the depth of the heating region. The
Well,
chart.
no, she's looking
The
for you, but I think she'll really like
maximum
those two.
column and also the column
She wants to talk. She
And
told
then
me yesterday, she's like, I haven't seen you
fires
in a while. I was
the-
like,
Oh, yeah, I want to talk to
So I've
her
just
too.
described where the
Because-
convection happens, so it doesn't move,
Yeah,
and also
let's
how
go,
strong
let's
it
go.
is.
Okay,
So
so
there's no
you are
change.
controlling the excitation of the gravity waves in the parameterization instead of letting it interact with the model.
Yes,
Okay.
there's still like the interplay with the zonal winds because
Yeah, of course, but the excitation doesn't change because you
Yes.
are essentially
yeah,
specifying
the
that.
convection is fixed basically.
Right.
Well, it's not
Okay.
fixed for like convective reasons, but like as far as QBO is concerned, the convection is constant,
Right,
right?
in the rest of the model, it works as usual, but as far as the parameterization is concerned,
Yes.
you are prescribing essentially the excitation of the wave. I mean,
Yes.
I know that the zonal wind also plays a role, but
Yeah.
in terms of the heating,
Yeah.
it's, and why did you do that?
Because Yaga, well,
No.
because it speeds up a lot as you go into like
Oh,
into
in
the
a warming
future.
climate.
In a warming climate, it speeds up
You
a lot.
we know
And
that. Yeah, in fact, the QBO gets almost angry.
yes,
In
so,
a for a CO2 experiment, it's almost angry.
yeah, so the idea was to stop it from speeding up, but
Yeah.
we didn't manage to do that because then we need to like change the zonal winds and that would just be complicated. But we did manage to slow it down a little bit, so.
Okay.
Right,
You try
yeah,
Firefox.
I understand why you do
Yeah.
that. Okay, this is all really interesting.
I mean, it's all sensitivity routes. I'm not saying like this is how to improve
No, no, no,
parameterization,
no,
which is
I'm
like-
just trying to understand motivation. You know, I know that there's a lot of things that you can look at
Yeah,
when it comes to gravity wave forcing of the
Uh-huh.
QBO. I mean, one thing that is
try
obvious is that you
just,
cannot get a good QBO just with gravity waves.
Yes.
You need
Yeah.
Kelvin waves, and
Yeah,
the only way you get,
it's worth trying. So
you
is
can
this, do you
simulate
have
that
a
if you're going
PowerPoint?
to have vertical resolution.
Yeah,
Now, we did a lot of studies on that, and well, plus all of the literature now is showing that you do need to have the
Yeah.
actual Kelvin waves. And what's probably more important, the Kelvin waves on a meaning with interaction, I don't think can be captured
Well,
Okay.
a lower vertical resolution.
okay.
Yeah.
kind
Is
of
there
like,
also the
who knows if it's,
northern hemisphere high latitude better reproduced with 110 layer version? So do you actually get a better like polar
Give it
vortex
the permission
response or
and-
something? Do people look at that?
There's been some look, I mean, what has been done as of 2 years ago is what Andrew Getterman published in our WACAM 6 paper. So
Okay,
that's Getterman 2019. And it's, you know, the northern hemisphere vortex is generally okay, but they are biased.
sometimes it.
Biases, and the biases are vary with the season. So
okay,
you are looking just at the winter time average, comparing that to observation. That's not too different. I mean,
Okay.
I don't know why you put error bars on that way, even they are statistically significant. But if you look through the winter, early winter, the Wacom vortex is too strong, then midwinter is too weak, and then it's back.
okay,
And it also, yeah, and that also seems to go along with the climatology of warmings.
okay,
So there is something that we are not getting right for the northern hemisphere.
okay,
Now, the northern hemisphere in principle should be easier to get because there are no gaps in the orographic gravity wave forcing as there are in the southern hemisphere. Southern hemisphere, you have a Palmer Peninsula, you have South America, and you have a big gap in between.
yeah.
where
Yeah.
in reality, the gravity waves force in those two places tend to converge into the vortex.
Okay,
You know, has been shown in a number of simulations.
so that's why you
But-
do this like
Yes.
smearing
So
out.
I
of the-
think that's why it is so hard to control the solar.
I think all those things.
Well, essentially in any model where
Yeah.
gravity wave parameterizations are column-based, which essentially all models.
Yeah, like most model have this strong Antarctic vortex, right?
Yeah.
That's what-
Much harder to get that right than in other hemisphere, and I think that may be one reason for it.
Okay,
Do the intervals. Here's the
That's
cross
all I have to say about
Okay.
it.
Here's the flux.
And I don't know how you fix that. I mean, ideally, you will have a way of estimating a refraction of waves.
You can have a way of
strong
specifying
core of
itself
this
consistent
hemisphere vortex.
with
But
or is
right now, there's nothing like that in the parameterization.
okay.
It should be very clear.
Julia was saying
This is the
something
part of
to
the
actually
code
put it,
that you would
imposing like a
You have
Gaussian
another way of
spread or
calculating.
something.
You could do that. You could. Now, the question of how you do that in a parallelized model,
Brings
not
me way
clear
on
to
the
me.
spectrum.
because
Yeah.
somehow the columns say
One of the
over
things
the
that-
Drake Passage and places like that
The
between say
parameterization
45
always
south and 60
So,
south.
the process
Right?
of-
Or 65.
If you
That
get
area
some
where there's only water,
Uh-huh.
right?
do the same thing.
That's where no, there's
We
no
have those, I
gravity.
think,
Gravity.
we already
We would
have a
like to
solar
actually
module. right?
allow some of the gravity
Can't
wave
be
flux
part of the same.
Okay,
to get into that area. Well, how do you do that? Well, you could sort of try to smooth the forcing, but you cannot do that in a parallelized model because one column doesn't know the other.
yeah.
So I don't know how you do that, and I don't know what Julio has said about it.
I know I got.
He was just thinking out.
Yeah, I heard a number of proposals to do that, but when it comes to implementing them in a very highly parallelized model, because now when we go to the cube sphere and all of these 3D parallelizations, then really you don't know. One column doesn't know
I know.
the other.
And I was told
In
that-
FV wagon, at least you know about all the columns in a zonal dimension because you only parallelize them down.
How do you do the transport? The other column, like this, the
I don't know
whole.
what the.
Oh, but for transport, you have to know. I mean, you
Yeah.
have to at least
You need to have
bring
the gradient,
adjacent
right?
columns.
So,
Yeah,
like,
the dynamical core has to bring adjacent. So that is somewhat inefficient part of it. I mean, this is the problem that transport is non-local, right?
Okay.
Because it depends on gradients. So you run into these kinds of difficulties. But for the gravity wave parameterization, I am not an expert in computing, but what people tell me is that, trying to do these things, make it inefficient.
Okay,
And so we have what we have.
But you can help us with the 93 level model too, maybe.
okay, like I did to just assess sort of sensitivity stuff, but like, yeah, I'm happy to help if I can.
One thing we could do is to fake it, say, even though there is no land between 45 and 60 degrees in the southern hemisphere, we're going to pretend there is sun to account for the fact that
Yeah,
there is some.
That would be the easiest thing, because you just prescribe a different topography for.
Yeah, but you can see how that might work, but how you justify it in a precise way, it's much harder.
Okay,
Anyway,
thank you.
I'm gonna get something to eat.
Yeah, we need to move at one point to the new model version with higher vertical levels.
Like coming from the UK, they have the UKSM has 85, it caps at 85
Yeah.
kilometer, and no
That's
one's been
fine.
saying like, which is, as long as you're not interested in mesosphere, it's fine.
Yeah, but that was the question, especially for aerosols, because they evaporate, the question is what happens above the
Yeah.
80 kilometers for SAI, and that's one thing that Nick wants to try testing.
Okay.
Yeah, too.
Yeah, there's been interest apparently in the whole like ER industry
Yeah.
community. Yeah, Karen told me.
Well, we should talk more about that.
But like, yeah, I do think like if your interest is in the stratosphere and troposphere, then capping at whatever it is, lower mesosphere should be fine. And then you have a higher vertical resolution.
Yeah.
So just like, yeah, what you're interested in.
But to understand all those differences, because that may be another new model again. CSM2, and then there's CSM basically 3.
I mean, that's basically what I've been trying to do, because there are all of those models and
Yeah.
every model shows a different answer, right? So
Right,
we're
and
just
then we
like,
can figure out what is the effect on.
Yeah.
And does it matter? I mean, if it's 10%, that may be fine. And then we have the microphysical differences, that's
Yep.
10%. But then at least it's only 10% or 20. That's maybe doable. It's not like. a
Yeah, no,
complete
that's fine.
science
So that's
thing.
why I just wanted to like, you know, someone should, well, it is presumably, it might be still model dependent, but still like at least some sort of quantification, right?
Yeah.
And I'm not
that's
sure like if actually if we went to high, if there's, you injected 50 closer to tropical pipe, if you actually might have a bigger
I
impact.
would identify the jets and inject.
Yeah, I know,
It's not that hard to do.
I know. So UKSM, so Jim is just injecting at the 60 north and 60 south now, and 15.
60 is
Too high,
ridiculous.
yeah, I know.
It's like, why do you want to waste that? Yeah, but okay, whatever. No, but yeah, I mean, Ben Kravitz had done some diagnostics, internal diagnostics on identification of jet location.
Okay,
But instead of injecting outside the jet injection location, they injected on the jet because they wanted to disperse the aerosols more.
okay,
And I thought, why would you do that? Because they thought that would show increase the efficiency.
okay,
But it's not all about efficiency; it's about controllability. If you inject it on one side or the other of the jet, because you get a clearer signal from one side than the other in the
Okay.
certain hemisphere, and then you should be better with your feedback control.
possibly, yes. I mean, it's one calculation, right? You just think that,
You do have to identify the jet, and that's the thing that they did. I wonder how they did it, but you do maybe have to have some kind of level for potential temperature.
you can just do zonal winds.
Yeah.
And potential.
Yeah, you can do this on the wind. We could ask him why he did actually in his study. I think they used even Wacom.
Oh, come on.
Yes, or come, but like, yeah, I mean, the question is like, what would be, because you eventually want to do a multimodal comparison, but then that's gonna be even more complicated.
Yeah, no, for now, it's more like just a feedback control.
Yeah.
Better if you do it that way. Do you get a better controllability?
Okay,
To me, at least. I don't know if, yeah, maybe we should discuss with others that idea, but nobody really.
I mean, from when they were looking at the differences between 15 and 30, for like if they are 50 plus 50 plus 50 plus 50 and 30 plus 30, the differences in the surface climate went smaller, but on a yearly mean.
And that depends on the model.
Yeah,
Because it
so,
depends on the. I had one question for you.
Yeah.
Sorry.
Go for it.
You know, I mean, I didn't respond at all to your recent talks, but the 58 level is performing worse, right?
It kind of seems, so it's difficult to quantify, but it does seem like it's not a large improvement. So I didn't show.
But even worse, it's even worse, because this is really this is the Wacom model in the background, right?
No, these black dots are observations.
Yeah, exactly. So the
So-
Wacom model is in the background.
No, this is the colors of the Wacom model
Yeah,
here.
yeah, that's what I mean.
Yeah, this is the music of 58.
Yeah.
Yeah.
So, the problem is that this is a much better representation of cross rate.
Yeah,
The
right.
gradient across the tropical. It can be just like, I don't think it's in the question.
Right, this one still doesn't.
This has 500. Why does it? And I have questions on that.
Exactly. So just to be clear, and I kind of
Yeah.
tried to, it's just like, there's so much to say. This is still a I think.
This is the problem of
This is-
68, and I have a suspicion that, you don't have the 93 here.
Right.
But the 93 does continue a bit higher
Yeah.
before it tapers off. And I think, anyway, I have to put 93 level and figure it out.
I think that would finally sum it up, whether that is the thing, whether that's the reason, whether it really is.
I think we should focus a bit on the 93 without regional refinement, because that's equivalent to the 100. June ran a 93.
I think we may have tried that, but I don't think, it might have been when there was still above, there was still an internal.
Yeah, so
And there's
and
a-
if we have the water vapor fix.
in this run, yes.
There's a water vapor fix.
Yeah, she ran this a month ago. When,
So
how
do
recent
you-
is the water vapor?
You have a water vapor fix in your run?
Water vapor fix, did we ever come up with fix for?
Yeah,
water
they
vapor?
had some energy thing stuff. that they don't dump it all in the stratosphere.
Grab some tea.
That was a long time ago?
No,
It's recent, then no.
so
I added
We did
dual
see
fix
that
and
Perfect.
I would
higher
think that the
altitude
the
fix.
high latitude is like.
And this
Maybe
one
I
should
could
have some
find out.
topography problem. So
I think we need to run a 93 level.
yeah, the latitude level, yeah, I haven't touched that for a while.
Yeah, I do have a version
there's a
now,
little bit.
but that's. I
Well,
have the topography fix. It's from
Yeah.
Cecile, it's one kind of version
Okay.
that I ran the 58
So,
level
you know, it's all
in
like.
the free
all
running
trade-offs,
version, and
right?
it still
Depending
has
what
a
you
way
wanna
too strong
analyze,
polar
if you
vortex
look
when I
better,
ran it free
Do a
running.
better version for that?
In
I don't know.
the free running 58 has
You're
strong
okay.
polar
Yeah.
vortex.
Yeah, so my question was, just, we don't
Yeah,
until we
yeah,
try
I
it,
just
so,
wanna-
are we gonna introduce more, are we gonna introduce other bugs that we don't know about? And as soon as we, we have to- So the 58 level, we've had a couple of things we found, and it's,
Yeah.
yeah.
Yeah, I
Some of
mean,
it
the
is-
problem is this 58 level, it's not even good enough for the QGLS.
Yep, that's
What
good.
is it good for? It doesn't produce a QBO.
Okay.
It's a little sensitive. I wanted to say, I wanted to keep everything
Okay.
spin.
No, you
No, that's fine.
But yeah, there is a question there. Is the 58 level getting better?
All right,
You should
everyone.
not, yes, you should not warm.
Welcome to the last session for CCWG, WAWG folks. There's a boundary layer session this afternoon if you really want to go.
No, that's enough.
Okay. So we've just got 4 speakers left. Home stretch. First speaker this afternoon, or this late morning. I have no sense of time. It's Valerie Uden. Oh no, we just had it. I shouldn't have said anything.
You broke it, man.
Yes, so,
Yeah.
Okay.
no, you got, I got this one, you got.
Oh geez. I don't know. The presenter.
One more time. You don't get it.
No.
Stop sharing,
Okay.
stop sharing, start sharing. Here, start a screen.
Is he sharing entire screen?
Yeah. It was working like 2 minutes ago.
Well, here comes something else.
And now try to go to the PowerPoint behind it.
Excuse me.
Go to the
Click on the PowerPoint, which is behind.
behind.
Yeah. There you go.
Now hit play.
There we go.
There it is.
We're good.
They said it wouldn't be done, but.
I don't know how to get rid of this stuff, I'm sorry. If I just press the button, I lost my presentation. Please, please.
We can do.
So, today I would
No,
like
hide
to
that figure,
talk
it's
about
a minus.
the ability of tides in the two-hole atmosphere model that we have in the United States of America. This is VacuumX climate continuity model of NCAR and whole atmosphere model of Colorado University and Novel Space Prediction Center. So my co-author on this talk, first of all, I would like to present myself. I'm Valery Uden. I'm currently working as a research scientist at the Catholic University of America and Global Space Flight Center ITM laboratory. And this is my first year on this course. And so my responsibility will be to develop observing system simulation experiment to support satellite missions of NASA. And so the reason why I'm talking about here today, so I just would like to give you some basically overview what kind of agreement or disagreement with observation of the data we have in the total atmosphere models, WAM and WACOM-X. So all the simulation will be so-called specified dynamics or specified meteorology. It means we have wonderful WWG observing system product like laboratory analysis of GEOS 550. We do matching or specify analysis tendency from the surface to 50 kilometers, run this model for several years, and do diagnostics of tide, main tidal modes, and also 24-hour oscillation and 12-hour oscillation to represent geographical maps of diurnal cycles and different vehicles. Just to remind you what we got 8 years ago. It was first paper of Nick Metatella written in 2014, and it was comparison between 5 million-atmosphere whole meter atmosphere model driven by meteorology of different reanalysis system. And I here just pick up a picture from this study and put DW1 as W2 distribution during very famous southern stratospheric moment of 2009. And at that time, you can see basically one on this basic on the upper row and WACOM-X matched to NavGen and nearer to the lower row, and you can see basically huge differences between the types. So later on, we fix this stuff, just basically updating nudging algorithm and take out aggressive nudging with 6-hour cadence relaxation time scale to 50 or how 3 days, and this can be corrected, but you can still some differences. And several years ago, John McCormack just recently published another paper. He compared 4 analysis, and I put here for stratospheric warming of 2010. This is days from January 1st until March, and you can see that WACOM-X plus DART and Japanese reanalysis, they simulate the similar microwave film sounding data, but we still have different answers. Even this model was constrained by MLS and cyber temperatures. So that's why we would like to get some essence why we're basically different and how close currently we can basically represent this. Oh my goodness. Okay, very sensitive. So what I plot here basically representation of average of diurnal tide 2 major mode DW1 and DE3. This is seasonality from 2009 2016. DW1 at 97 kilometers, DE3 and 105 kilometers. Cyber, of course, we cannot do basically because due to local solar time sampling, we can use 60 days composites and move 1 day running window to get estimates of tidal amplitudes in the classical manner, like Jeff Forbes proceed, and this is basically the results from the Sumerian oscillation, very famous Sumerian oscillation amplitudes of migrating diurnal tide and maximization of non-migrating diurnal tide around June, July, August, September, July, August, September. And you can see if you look at the WACOM-X geos and WAM geos, so we're trying to pick up basically all this variability, which is quite good. A little bit less WACOM-X driven by geos comparing to WAM, and probably I will attribute and discuss later to differences between gravity wave physics parameterization and also two different dynamical cores. I need to mention that WAM use spectral dynamical core. WACOM-X is the finite volume on rectangular grid. For non-migrating diurnal tide, if you compare cyber WACOM-X and WAM, so you can see basically the maximum is approximately the same, a little bit towards September in WACOM-X. But what's interesting for me, you can see both models produce a similar shape of seasonality during these years. Cyber doesn't produce. So probably because non-migrating diurnal tides is basically associated with convective latent heat release forces diurnal variation over the land. So both models have quite similar convective parameterization and latent heat releases, and that's why we can probably conceive a similarity. And if we go to the semi-diurnal type, so this is again cyber estimates average 2009, 2020. This is semi-diurnal migrating mode number 2, and this is VacuumX representation. This is 110 kilometers, and this is all years from the SD VacuumX run, and this is only years which has major stratospheric warming events. And you can see here that we have one more feature of event-driven variability in the semi-diurnal type, and this particular height in the above 110 kilometers. We have amplification of semi-diurnal type during stratospheric warming events, which is exceed actually all maximum amplitudes of type at this height during all season. So this is basically very, very interesting and powerful observational metrics that we need to take care if you would like to simulate seasonality of semi-diurnal type in the low atmosphere. And then here I just plotted 125 kilometers, one major representation of semi-diurnal type amplitudes during stratospheric warming events. And this is just average our January, and you can see how much you get differences between semi-diurnal type. You get much less differences in the 8-hour and 24-hour type. So the major effect of the stratospheric warming events is in 5 days after onset of warming events, you have amplification of the semi-diurnal type activity. So this is basically sensitivity of tidal dynamics in one. Now is again semi-diurnal type migrating mode, and this is DW1. But here I made in one sensitivity to interpolation or turning off non-orographic gravity waves to give you some ideas. If you don't know non-orographic gravity waves, how your tides looks like seasonality. So this is cyber again, 2 migrating modes. This is one with non-stationary gravity waves. So it gets basically reproduce of maximum at the appropriate latitude. This is 105 kilometer height. But if you don't have gravity wave, so you immediately screw up seasonality of your tides and amplitudes of tides. And also not only for semi-diurnal tide, which is most sensitive to the ground flow on which you tide propagate from the stratosphere to the MLT, but you have also basically different answers for diurnal migrating tide. For instance, it tends, if you don't know gravity waves, it tends roughly produce equal amplitudes during March, April, and September, October. Light data doesn't show this. So basically, this is I show zonal mean winds at this particular cross-section seasonality. If you don't have gravity waves, of course, you don't have basically wind reversals, and you screw up the behavior of your semi-diurnal type in the model. Now I just, of course, the tides is basically propagated on the ground flow. So it's basically our estimation line. This is basically deviation from daily mean. So how our daily mean looks like, in particular in the equatorial region. This is representation of the temperature for one particular year, 2009. This is seasonality of zonal winds and averaging between 10 south and 10 north. This is the mean temperature. You can see basically differences between VacuumX mirror and VAM mirror. So if you look at the basically counterpart of a cyber time data, so you can see basically what the current VacuumX what basically running with demo doesn't have a lot of variability and have persistent warm bias. So warm bias at around 120 kilometers up to 30K degrees. So, and of course, icon and cyber agree to each other quite nice. And with this deviation, I didn't put one distribution in this region, but it's much better comparing to a vacuum. So if we would like to do observing system simulation experiments with twin model experiments, so we need at least to fix some biases, systematic biases of zonal mean dynamics in technology. And to look at the extratropical winds, we look also seasonal behavior of one GEOS and vacuum X mirror, and you can see the similar, basically, very smooth behavior in this region comparing to oscillation, which is reproduced by spectral mode. I would say this two model, of course, use two different gravity wave parameterization, but I think we need basically to somehow in vacuum X, especially to fix these biases and something reproduce like Europe reference atmosphere, which is we use many times for comparison of our zonal mean environment. Yes, okay, and so this is again, I just would like to present you difference in the zonal mean flow now in temperature. And the bottom cent of this, 2 cents of this, but basically model, of course, disagree to each other, but they also doesn't agree with Europe atmosphere. How to check how valid Europe atmosphere, this is 93, 97. So you can use just Katatabend data, which is samples the similar phases QBO, and I would say this Katatabend remind you more of comparing distribution of interannual variability on zonal winds seen in both models. The most interesting feature is also interannual variability of diurnal tide modulated by QBO. Here I put cyber temperature cross-section at 95 kilometers and the stratospheric zonal wind between January 2009 and January 15. And you can see if you have westerly QBO phase, so you have approximately 2 times on 1/2 times more stronger diurnal tide amplitudes. This is another metrics for diurnal tide oscillation. And this feature actually quite nicely reproduced by both models. I pick up here only vacuum mirror 2 comparison. And if you look at the longitudinal variation, how this seasonality for easterly, westerly QBO phases reproduced by Cyber 1 and vacuum X. So you can see this 4-peak structure during March, April. So just you need to remember what we was thinking about usually that non-migrating tides is maximized during September, June, July, and August. But actually, you have a lot of non-migrating pinching during March, April. I will skip the slide here. And this is basically comparison of one representation of diurnal 12-hour, not decomposition on the longitudinal mode, just only diurnal amplitudes around the sphere. And you can see this is, again, to be west, to be east, you can see basically modulation of diurnal oscillation, diurnal oscillation amplitudes and amplification during westerly QBO phase. And if you look at the similar counterpart from tidal data, so you can see the similar features. So I just did several set of experiments involved, trying to understand what kind of mechanisms responsible for this. So first of all, this is basically run for 2 years with gravity, non-stationary gravity waves. This row shows run without non-stationary gravity waves. So you can see that probably resolve waves still impact on the diurnal tide distribution. So you see difference between to go west and to go east. But if you nudge model only below tropopause, with signature differences of the diurnal tide modulation by QBO dynamics is disappearing. So it means I go to my conclusion slides, that basically the importance of background flow for propagation of semidiagonal diagonal ties we need to recognize, and we need basically to tune up our model to reproduce major observed features of the zonal mean dynamics in the MLT. And we are lucky with last years. Now we have, in addition to the cyber MLS, we have ICON and gold data. Mostly now we rely on ICON. And I just show you comparison of the vacuum matches sampled along ICON orbits for different local solar times, which is March 2020. And you can see how all this feature in the MLT region with meridional means can be reproduced as vacuum XD. Which means that we now fixing some biases in the model, think about how to simulate jointly temperature and wind data, at least in the region between mesopause up to 150 kilometers. Thank you very much. And if you have questions.
I think just in the interest of time, we'll move on and go to our next speaker, Mijong Park. You can stop sharing and then she can.
Okay, sure.
Next. Thanks.
Okay. Today I'll be talking about simulations of the QBO using the 2-degree version of the vacuum. I'm really excited to talk about this today. I'm Mijong Park, and I'd like to thank Doug, Orlando, Sasha, and Yaga at NCAR, and Jessica at JPL for their contribution to this work. So the QBO is the dominant feature in tropical lower stratosphere in a zonal mid-zonal wind. And the global models have had difficulty simulating reasonable QBO in the past. But now we have many models can simulate good-looking QBO, like the one you're looking at right now. The top figure is from the paper from Garcia and Victor, 2019. And they use vacuum 5.4 with 110 double vertical layer with 1 degree horizontal resolution. And you might wonder then, what is it? How can we simulate QBO successfully? So the number of papers talk about what we actually need to get this QBO. A couple of things you want to remember is adequate horizontal and especially vertical resolution, and the way of simulating tropical convection and subtractive wave temperature, which Eva just talked about. I really like her talk. And just as an example, what does QBO look like in vacuum 70 level? This looks a lot like Eva's figure. So not having enough vertical layers, QBO, especially westerly, does not come down low enough. So we had this idea, it's not my idea. So how about we maintain this 110 vertical level and use 2 degree horizontal resolution instead of 1. And this is what it looked like in the model. Top figure is from vacuum 6, 2 degree version with 110 level. We have really good looking QBO. I'm really happy about that. So now we have pretty good QBO in the model. So let's just remind ourselves. High vertical resolution is important because to be able to generate reasonable QBO in the model, a broad spectrum of atmospheric waves are really necessary. And for example, in this paper talk about even waves with vertical wavelengths of 2.8 kilometers longer. That's pretty flat. And the second point I will make is by using 2 degree instead of 1 degree horizontal resolution, we can save a lot of costs. So we can apply this model to study climate scenarios in longer period. So one idea we had, or one project we had was, how about we just assume there's El Nino all the time, and there's La Nina all the time, or there's no El Nino and La Nina. We call it perpetual El Nino and perpetual La Nina. And we talked to Yaga and Sasha and CGD, and we learned about this project called QBOI and so QBO. When this happened actually in 2018, number of modeling group, they try to look at how the ENSO modulate the QBO. This plot is showing just the SST input over Nino 3.4 region. During perpetual El Nino, the seasonal cycle repeats as El Nino's condition, and La Nina lows SST repeats the seasonal cycle. So now let's look at the QBO from this 2-degree vacuum 6 run. Top figure is for perpetual El Nino condition. Bottom plot is for perpetual La Nina. As you can see, for El Nino condition, QBO seems a lot faster. And for La Nina is slower. And either average or base case is in the middle. And now that we have, okay, vacuum 6, 2-degree version of El Nino, La Nina case, average case. And we were able to get this model output from QBOI, so which was done in the past with 1-degree horizontal resolution. The idea was to compare these two and make sure 2 degrees is okay, we can use it. But as you can see in the next figures or with this one, there's some difference. Let me just get into it. First of all, these are comparing QBO amplitude in these two models. On the left is 2-degree model. There's 3 lines. Black is average, red is El Nino, blue is La Nina case. As you can see, during El Nino case, QBO amplitude decreases. And the maximum of QBO amplitude is around 25 or 26 kilometers. And compared to 1-degree output on the right-hand side, the amplitude maximum is a little bit higher, and the amplitude is stronger. But more importantly, during perpetual El Nino case, QBO amplitude doesn't simply decrease. And around 20 kilometers above, QBO is stronger, and below is weaker. It's different. We're scratching our head at this point. And how about the period? We've looked at the previous slide. Perpetual El Nino for 2-degree case, QBO becomes faster. Is that true? So I'm comparing these two plots. On the left is vacuum 6 2-degree. On the right is 1-degree. Once again, black is for average or base case. Red is El Nino and blue is La Nina. Let's look at the plot on the left. The red is El Nino case. The average period for QBO is only 18 months. And for La Nina is 35 months. Okay. And for 1-degree, that's not the case. For La Nina, QBO gets lower, which is 35-month average period. And for El Nino, it's slightly longer than the base case. And we're really scratching our head at this point. We're so puzzled. And there are 2 things I wanted to point out here is that there were studies related to this ENSO or doubling the CO2 or quadrupling the CO2. When the troposphere gets warmer, we expect QBO gets shorter, so there's stronger convection and generates more waves. And the second, we went back to this literature, looked at QBOI and ENSO model runs. There are multiple models. Some models show shorter period, some models show longer, or so there's no change. So there's a lot to learn here, and we didn't know what's really going on here. So I've been reading many papers. I didn't know how to approach this problem. So I'm sharing with you there are 2 plots. On the left is a figure from Santa around 2021. They looked at, okay, what drives the QBO then? We have to know, to understand QBO, what's behind it. So they did zonal mean, zonal wind tendency analysis. On the left plot, there are multiple colors. There are 10 different terms. And I just put two arrows. One blue is moist convective wave drag, and the green one is EP flux divergence. And the orange is something called transient advective term. I don't know all the terms, but there are a few terms that are important driving the QBO in the stratosphere. On the right-hand side, this figure is from, again, Garcia and Victor, 2019. The black is zonal wind, and the red is gravity wave drag term, and blue is EP flux divergence. So what EP flux divergence and gravity wave drag does, every time there's zonal wind acceleration, they contribute to QBO. Okay, so let me maybe reproduce the same plot with Wacom 6, 2 degree, and then Wacom 5.4, 1 degree. The top plot is Wacom 1 degree, bottom is 2 degree. It's the same way Rolando and Yaga did a plot. The black is zonal wind, and red is gravity wave drag, and blue is EP flux divergence. Those two wave terms contribute to this wave, the zonal wave acceleration. Okay, one thing, maybe the blue at the top plot is slightly smaller, but it's not significant enough to give us an answer. Oh, this is causing it. So we're still looking at these other terms. And I will still read the paper. And there were a couple papers, but Isla's paper looked at, this paper came out 2011. She looked at the response to ENSO using Canadian atmosphere model. And what they found out was during ENSO, the troposphere gets warm and the tropical upwelling increased and it gets cooler. Is that true? So I wanted to see if this is the case for Wacom 5.4, 1 degree run. So I made this climatology for this is 1 month, December, for 1980 through 2014. So on the left is El Nino case. Upwelling is a lot stronger than average or La Nina case. Especially these paper talked about the wave drag is especially stronger in the southern hemisphere instead of the northern hemisphere. So if you look at the whole stratosphere, the red is a little darker in southern hemisphere. Okay, this seems to be related to El Nino, little bit acting differently 1 degree. Now let's compare then upwelling in all the scenarios. So I made average the tropics, low stratosphere, so 68 hectopascal pressure level. There are 6 lines. The darkest and thickest red line is the 1 degree El Nino case. The upwelling is really strong, stronger than any other runs. The thinner line, orange, is El Nino case for 2 degrees. It's not as strong in 2 degrees. And is that true? Is it getting cooler? The bottom plot is the temperature. Yes, it is too cold. So there's a paper came out in 1997. There's a one line I copied and the bottom you can read it. The ascent in the tropics is comparable but opposite side. So when the upwelling is too strong, QBO does have hard time transiting to a different base. That's what, I don't know, I can maybe explain better. So we found something really different in 1 degree run. And what else? Can we look at other differences in the model? So this is a figure from Rolando and Yaga's paper looking at the zonal wind climatology for December, January, February. So on the left plot and the middle plot should be the same. This is exactly the same model. Wacom 5.4, 1 degree is the base case. Okay, this looks pretty similar. And the 2 degree average case, can 2 degree do a good job in dynamical field as well? So I was just talking to Eva, and she commented to me that 2 degree maybe does a little bit different in high latitude and not the tropics. There's some difference, but looks okay to me. And now, this is my last plot. What if I take differences between 1 degree, 2 degree, all this dynamical field for El Nino, average, and La Nina case? Is there anything different for just for El Nino? So on the right, there are 2 plots. Top plot is average scenario, and the bottom is La Nina. The differences between 1 degree and 2 degree. So I put plus signs in subtropics, but this is jet stream is stronger than 1 degree, they look pretty similar, but they don't carry phase La Nina average. But if you look at the plot on the left, this is El Nino case. For some reason, the zonal and zonal wind difference is bigger in the tropics. So something is going on for 1 degree El Nino case in the tropics. So this is messed up, right? So this was a fun experiment using 2 degree version of vacuum 6, similar in the QBO. QBO looks reasonable. And we try to understand the difference between El Nino case in 2 degree, 1 degree. We don't understand fully, but we made some progress. There's more work to do. And we're excited to have this model configuration we can use more clinical studies in the future. Okay, that's it.
Thanks, Michelle. Yeah, Martin.
I have a question.
Yes.
Did you compare the QBO in the 2 degree model with error incidence?
Yep.
How do the amplitudes and periods compare?
They look pretty, so I actually compared with error 5.
Okay.
And they look, there are 2 things. One is in 2 degree, QBO amplitude is little weaker.
Okay.
Because wind speed is weaker. And the maximum altitude is slightly lower, but they look reasonable.
Is there evidence of this really strong modulation in the period in the observational data set? Like, so when you look at the observed winds, El Nino, La Nina time series, do we actually, is there a strong evidence of the period changes that? I mean, this is a very big change you're showing.
We've seen the model because this professional El Nino, we're just making this up. So the real atmosphere has El Nino, La Nina, and the initial case. So this doesn't really happen in the observation. But if you look in the future or warmer climate, for example, doubling the CO2, QBO speeds up, either 70 level or more, but not in observation. Yes.
Sure, yeah.
I'm sorry, no, if you want to go on, we can.
It might be good to go on.
Yeah, go on and we can talk about it.
Thanks. We'll keep it at 2 questions. Thanks, Bijan. Well, Orlando's next, so you can talk anyway.
I could have given them my time, but. Okay.
Yeah. Do you have your laptop? No.
No, it's supposed to be on the computer. I sent it to Elizabeth and she told me she had it.
Sorry. All right. Who's got?
Right outside the door there.
Dan,
There was.
When you, Ren, thanks. Grab that laptop. We can pull up real quick.
We can switch order.
Do you want to switch
Or I'm
order?
just wondering.
Yeah, okay.
Why don't we, yeah.
Why don't we switch order? Everyone online is gonna do some, but unless it's.
Keep up, but.
Okay. Okay. Wow, thanks. That's good.
I will pass.
Oh.
You're gonna be in the La Nina or El Nino phase?
Well,
18 months.
It's not a realizable experiment in the real world. You don't have to pay for
But you should be able to. You have periods of La Ninas, periods where you have 3
Right.
or 4 La Ninas in a
But,
row. and then you have-
That doesn't determine the QBO period required. So, I mean, it's conceivable you could try to look at that. I don't know what you're gonna do.
It seems like 18 to 40 months. Is it?
Your state. The problem is El Nino lasts essentially a year, QBO is the 2-year period, so how do you set up an observational test?
And then how I go.
And how do I advance this? Do I have?
Well, I'm working on getting it full screen. Good lord.
No, on full, there should be a little, where that recording tab is, there shouldn't there be a little green thing?
Yeah.
But you could do
Or
it
download it and-
from the, you should be able to go on, let's say, let's see here. Otherwise, we can just show it this way and be done with it.
Maybe we should do that. I have no easy way.
Yeah, screw it.
I don't usually do this, so.
Now, I don't have a way of advancing this slide, so you're gonna have to do it for me, unless you know.
Why don't you start talking and then I'll put it up here for you once I try. I'll keep trying it.
Yeah, you can put it.
Okay, I'll keep trying.
Oh, you can do it on your next one. Anyway, I'm going to start talking. So next slide.
All right.
Right, so Jen and I have been looking at the difference in the QBO in the 5.4 model. So this is a high vertical resolution, 1 degree horizontal resolution, 500 meters vertical. And we had a couple of runs that we had made for the QBO-I intercomparison a few years ago, which then COVID intervened and we didn't do anything about it. But and we knew that the QBO was stronger when you run Wacom with couple chemistry than when you run it without couple chemistry. So what I'm going to show here is a comparison of two identical simulations, same boundary conditions, same gravity wave parameterization tunings. Everything is the same, except for the specified chemistry run. We just use the ozone fields and other chemical fields are the repeating seasonal cycle from the couple chemistry simulation. And the couple chemistry simulation is fully interactive. So in this talk, what I am going to do is to examine the effect of having that interactive chemistry on the evolution of the QBO. Page down. Okay, so this is the QBO in both experiments. Shows the zone of wind at the equator and essentially average over 5 degrees on either side of the equator. One on the left is what I am calling experiment 1. That's QBO experiment 1, which is essentially present day climate, but doesn't have specified chemistry. The one on the right is exactly the same thing, but now with specified chemistry. If you look at these things, the QBO looks somewhat similar. And it looks realistic. The QBO winds descend all the way to the lower stratosphere. And there is somewhat larger amplitude in the couple chemistry, as I will show you in a second. This also happens for the temperature perturbation. The period, however, remains about the same in both of these simulations. So what is going on? Before I show you what is going on, I wanted to show you a comparison of the QBO amplitude and phase structure in both cases. Again, the case with no chemistry on the left, the case with chemistry on the right, and this is just a coherence analysis with the base point where that little triangle is. So it's about a little bit below 10 hectopascals and the equator. And the phase structure looks very similar. The QBO amplitude, however, is especially in the lower stratosphere stronger when you have chemistry. That's the one on the right. I can do the same thing with a coherence analysis, but now I'm just looking at a vertical profile at the equator, so you can superimpose one curve on the other and look at the difference a little bit more easily. So on the left is the coherence analysis for zone of wind. On the right is the coherence analysis for zone of wind temperature. And what you see is that, well, you see these pretty significant differences. Temperature, the temperature signal of the QBO is about 30 to 35% stronger in the lower stratosphere and about 15% stronger in the upper stratosphere between 20 and 40 hectopascals. The U signal is not appreciably stronger in the lowermost stratosphere, but it builds up as you go into the upper stratosphere. And by the time you get to 10 to 40 hectopascals, you are anywhere between 10 and 20% stronger. The phase behavior and the period are very similar in both cases. So what's going on? What causes these differences? Well, the obvious culprit, of course, is one simulation has it and the other one does not, is ozone. And what I'm showing here is the QBO in ozone, Wacom on the left, Saber on the right. That's about 20 years of Wacom data. I'm showing only 10. And the Wacom simulation were actually 30 years. Saber has a data set of about 22 years now. Again, I'm only showing 10. So that it's easier to compare the two things. But what you see is essentially a QBO in ozone that is pretty much out of phase in the lower and upper stratosphere, and that descends as the QBO winds descend. And the amplitudes and otherwise the rest of the behavior is very similar in WACON as it is in this set of observations. So we're pretty confident that we are doing a good job with the QBO and WACON. So what accounts for this behavior? Well, I'm just going to go through this very quickly, but it's very well known that essentially it's driven by zonal mean advection of ozone in the lower stratosphere and NOx, excuse me, in the upper stratosphere, which is affecting ozone chemically. So the idea is in the upper stratosphere, above about 20 hectopascals, ozone is photochemically controlled, so it's not going to respond directly to advection, but it is going to respond to the advection of NOx, which in turn affects the loss rates of ozone. So in the upper stratosphere, whenever you have upwelling, you have high ozone because you have low NOx. In the lower stratosphere, it's the other way around because there it is dynamically controlled and you have positive upward gradient of ozone. So you see this anti-phase correlation. This is all very well known. It's well reproduced in WACON. So insofar as this is going on, what is it doing to the heating? And what I am showing here is the on the left. These are both in the of course in the model with interactive chemistry. On the left is the coherence analysis of the ozone anomaly associated with the QBO in terms of the ozone fraction. That is the percentage with respect to the background mean. And the right is the same thing, but for short wave heating due to ozone. The reason I presented it as fraction rather than as actual units is to emphasize the fact that in terms of the percentage variation, the local variation, it is much larger in the lower stratosphere than in the upper stratosphere. So that stands to reason then that if when it's going to see an effect of the specified chemistry on the QBO, we will see it mostly in the lower stratosphere, which is what we have seen before. So how does this work? So here is a very simplified linearized analysis of how it might work. You start with a thermodynamic equation, linearized, same thing for the ozone heating, approximate ozone balance, and then combine these equations, and you get that third equation there. You can solve it for temperature, and what you see is that the relationship between vertical velocity and temperature is now modified by the by ozone heating. When you actually use this formula to do some calculations, or before I show that, you can compare that what happens with ozone heating. In essence, this is looking like an increase in the static stability of the let me go back. This is looking like an increase in the static stability of the atmosphere. It's acting that way, even though it has nothing to do with static stability. What is happening is that the ozone heating is reinforcing the positive temperature perturbation associated with downwelling in the QBO, and vice versa, of course, in the easterly phase when you have upwelling. So I did a calculation, and what I did is to compare the ratio of the perturbation in temperature when you include ozone to the one when you do not include ozone, and assuming that the vertical velocity is the same in both cases, which it really isn't, but for the sake of argument, that should be the ratio of the temperature perturbation associated with the QBO in the case with chemistry to the case without chemistry. And here are some typical values at different pressure levels on the left. The ratio is given here in the right column. When you go to the actual QBO, as determined from the model by coherence analysis, these agree actually quite well. Now, before you get too excited about this, there's a lot of things I have left there. Most importantly, the fact that when you modify the QBO, you modify the QBO temperature and wind structure, you modify wave forcing, you modify vertical velocity. So in a more detailed analysis, you will have to take all of those things into account. The only point of this is to show that, in fact, if you have ozone heating, tends to reinforce the effect of the mid-meridional circulation on the temperature signal, and therefore on the entire QBO. In the interest of, I will go to the summary in the interest of time. So what I have shown here is that when you use Wacom with coupled chemistry, when you have a realistic QBO in all of the important parameters, and you have larger amplitudes than when you run exactly the same model, but with an ozone field that does not change in time, except for a seasonal variation. We see that QBO in ozone modulates ozone heating, especially below the middle stratosphere, where these perturbations are important with respect to the background. It amplifies the temperature perturbation by 15 to 35% depending on altitude, somewhat less in the wind perturbation, and that a simple linearized analysis is consistent with what we are seeing in the model results. And that's it.
Yeah, Joe.
You say below 20 hectopascal, but how low is this effect?
Yeah, I mean,
All the way down to the
I'll show you that.
ponds
Yeah.
or-
Let me get back.
Thanks.
Oops. So here is temperature, and you can see this is about 20 hectopascals. It's right around here. So this entire area is the temperature response is modified. This is without coupled chemistry. This one is with coupled chemistry. So that value is anywhere between 15 and 30%.
And then below 60, it drops.
Yeah, and then essentially goes to zero down here because there's no heating at all. And up here, the heating comparatively is a lot less. But insofar as it changes things, it actually decreases the amplitude a little bit. But I was trying to emphasize this stuff in the lower stratosphere, right? Where essentially is mean advection modifying ozone and also modifying the temperature perturbation through the perturbation in ozone heating. So that seems to be what is going on there. Okay.
So your sigma is 28 months, sigma.
The period is about 28 months in both cases. And there's a lot of stuff done with QBO and ozone and period that is all over the place. In some cases, the period decreases, some increases, in some it doesn't do anything. In Wacom, the period doesn't change appreciably, whether or not you have ozone chemistry. What does change is the amplitude. Like,
Yeah, so it means
a non-trivial amount.
It means that numerical level prediction model which uses linearized chemistry
Yeah.
probably wrong. We need coupling.
Well, I mean, the basic physics of the QBO you can get without ozone coupling. The point is that it's an interesting thing that if you are ozone, you will get this amplification of the QBO below the mid-stratosphere. Okay.
Yeah, let's move on. Thanks.
Yeah.
I'll give the last presentation.
Yeah, I got it.
Can you actually get to stop sharing? Yeah.
There's a lot of it. I see, and I haven't done. You have to finish a little bit, but you should.
I can-
parameters
I
to
got
get
it.
a
I'll just keep- I'll just
to
keep
make
it.
the major picture.
Yeah, just keep me out. Just keep me out. We'll figure it out.
And that's the thing. That and the fact that the
Super exciting.
velocity-
Okay.
No, no, thanks.
Thanks, everyone. I can do this pretty fast. This is work I've been kicking around for a couple of years, and it's sort of whenever I have an extra minute. So this started us trying to understand how circulation change shapes global, like zonal mean even responses to forcings, and it ended up being the case in the last few months that I realized I actually needed to pull back from that and even just look at things from a more fundamental climate perspective. So if you were hoping for stratospheric dynamics, that's not where this is going to go, because that's just not where the research needs to be. So I just want to briefly motivate this work to talk about the circulation, not the circulate, and climate sensitivity. So there's a lot of studies looking at greenhouse gas, idealized experiments with climate models that show that things like habit cell expansion and changes in mid-latitude eddy heat fluxes scale with climate sensitivity. So you can see here that as models tend to have a stronger climate sensitivity, the Hadley cell expands more. As they weaken their temperature gradient more, they tend to weaken the eddy heat flux. And there's also connections between both the cloud response and cloud biases, especially in stratocumulus decks and models. And so the goal of this really is to try to understand, how do all these things connect? Is the circulation a passive response on for the ride here, or is it actually an active feedback shaping the climate response? Because if it's a feedback, it'll also scale with climate sensitivity. This is a very simple experimental setup. I have a 2-degree Wacom-FV with TSMLT. I'm happy to talk about this configuration. It's not a standard one, but again, I ran 2-degree because these are 100-year simulations and I didn't want to waste core hours on a harebrained idea. And so the idea is, I have a pre-industrial control run for 100 years and I archive U, V, and T every single time step. It's a lot of output. Then I apply an abrupt 4 times CO2 forcing, and it's a freely evolving model. But then I, in another abrupt 4 times CO2 run, constrain the eddy U, V, and T and zonal mean B fields to this pre-industrial control climatology, which means my zonal mean U and T become my freely evolving parameter. So there's a couple points here. I'm basically replaying the pre-industrial control variability in eddies and the zonal mean like Hadley circulation. I can't constrain zonal mean U and let zonal mean T evolve because I get inconsistencies from geostrophic balance. You have to choose some kind of consistent parameter space. So this is very much a zonal mean perspective, that the zonal mean is the fundamental response and the zonally resolving. Yeah, there is a forced component to that, but that's not the fundamental one. You can understand climate change from a 2D model. So the goal here was to keep things simple. I'm going to call this the 4 times CO2 response and this the radiative convective response because I'm restricting the circulation from changing. The reason we do every time step and a few other details is because this is a very big forcing and the circulation does not want to stay the same. So it's worth just looking at the data to understand just how this pieces together. So this is minus 100 years relative to the CO2 forcing and then to 75 years. The reason I'm restricting myself to 75 years is in this RC run, the AMOC fully collapses, which is kind of interesting. So it's a big enough forcing. So suddenly there was negative changes in 4 times CO2 over the North Atlantic. So it blows up over here, but the key is I can get a pretty good measure of climate sensitivity from the first 75 years using the Gregory method. And this is where I realized this was not going to be zonal mean dynamics. There was going to be some actual like old school climate stuff. Is when you restrict the circulation from changing, you get 25% more climate sensitivity, which is strange. How does the circulation response actually change your global mean surface temperature response? That is not what I would expect. I usually think the circulation moves heat around. It can't just like fundamentally change things, but it does. And this is a significant difference. Like this is a 99% confidence interval. So this is big. So this is basically the surface air temperature response in the run. So here's our total response from 4 times CO2. Okay, you get polar application. I'm showing the zonal mean of all of these down here just to guide your eye. So you get maximum warming at the poles. The RCE response gets you a little more warming in the mid-latitudes and tropics, but it gets you almost double the warming at the poles. So when we restrict the circulation from changing, the poles basically blow up. And if you take the difference between those two curves, you can just call that the circulation-induced response. And of course, you see there's then a huge cooling by the circulation at the poles, but there's also cooling everywhere. And it's especially aligned with these sort of stratocumulus and sort of mid-latitude storm track regions. The key is there's no place where the effect of the circulation is to warm. It's always a cooling, it's always a damping on global warming. And so that kind of lends our analysis to understanding this as a sort of diffusive response. I did want to bring in clouds, and I never look at clouds, but I thought this was really interesting. The total response and cloud radiative effect. Cloud radiative effect, you compare the scene with clouds to the scene without clouds and look at the differences in shortwave and long wave. So this is the total total cloud rate of effect. So where it's red, the cloud rate of effect is sort of forcing a net warming, where it's cool is sort of a net cooling. And this hatching shows you where there's either big cloud fraction increases or decreases. So this is not significance. This is the actual cloud fraction itself. I'm sure there's a better way to do this. But the total response is kind of complicated. There's this negative change at the poles, and there's some positive changes in the mid latitudes. But you know, there's a lot of zonal asymmetry. The nice thing about going to this zonally symmetric versus eddy regime and looking at the RCD versus circulation response is you get a much more robust picture. The RCD response when the circulation doesn't change is just a big increase in cloud rate of effect and a big decrease in clouds. So this is literally the cloud decks are getting wiped out when the circulation doesn't change. And that's not just the stratus decks, that's also the mid-latitude storm tracks. You'll notice that there's this negative cloud rate of effect change, but no change in cloudiness at the pole. Because cloud rate of effect takes into account clear sky changes, and there's so much albedo change and sea ice loss in this run, this is not a great way to look at things because your clear sky changes are getting quite a bit different. But you can kind of tell that, you know, the cloud rate of effect is really capturing the cloud changes in the mid-latitudes and tropics, but something's different at the poles. The circulation rebuilds the clouds. So the effect of the circulation response to global warming is to basically rebuild the cloud decks, although it doesn't quite overcompensate. So I wanted to look, okay, so I guess what I wanted to say is the key is that the circulation's operating in the tropics and mid-latitudes to rebuild clouds. And I think it might be related, especially to boundary layer processes, because that's where a lot of circulation effects we think have an impact on clouds. So, you know, the reason the stratocumulus decks are in these regions is partly because there's strong subsidence in the atmosphere. That sets off a capping inversion in the boundary layer, and then you get these sort of plumes and stratocumulus clouds. And so I looked at the vertical heat flux just across sort of the capping layer inversion, and I think this is just the key part here is to look in this region. The total is sort of a near zero change. The effect of RCE is to basically weaken the heat flux, which I think is basically wiping out the capping inversion. So you can imagine that even though we're restricting W, the background temperature in the atmosphere is warming, and I think the background gradient is sort of reducing in this region. And so what's happening is you're just sort of wiping out the capping inversion, and you're also drying out the boundary layer in the RCD response, whereas what the circulation seems to be doing is sort of reinvigorating that downward heat flux and also moistening the boundary layer. I haven't thought a bunch about this in great detail, but I think this is sort of the path to try to understand that effect, and I think maybe it's not so complicated. The interesting one is the poles, where I don't think it's the clouds. I think it's purely the eddy heat flux. And this has been proposed plenty of times, and plenty of folks have looked basically, you know, as the temperature gradient weakens, if eddies are diffusive of temperature to the poles, they're just going to mix less heat towards the poles. And so the idea here was to say the RCD response, which is really the driving response for circulation changes, we can understand the eddy response as a diffusive response to that background driving temperature change. And so the black line here at all latitudes shows you the eddy heat flux change in the troposphere. So there's a reduction in response to 4 times CO2 here. It's a little more complicated in the southern hemisphere, and we can talk about that. But the key is that when I train just a diffusive operator on the background temperature gradient in the pre-industrial control and apply it to the RCE changes, I get this huge decrease in polar eddy heat flux. The reason it's so outlandish is because part of the response to the circulation is to also change the diffusivity, usually by reducing the eddy activity or shifting the storm tracks. And so we expect an adjustment process. What I think is cool is that if you just add up the polar net rate of flux in the RCE run and the 4 times CO2 run, the response, the difference between them looks like this 4 times CO2 eddy heat flux response. And so what I think is pretty straightforward to say is that it is that reduction in the eddy heat flux that's that's really reducing the warming you get at the pole. And that's some things that folks have been talking about, but I think we can actually quantify in these kind of runs exactly how much that matters. And I think it ends up basically reducing the pole amplification by a factor of 2. So just to kind of summarize, this is still kind of a mess and it's a work in progress, but I think what this shows is that the circulation response to climate forcing is a negative feedback. It damps warming everywhere at the surface. Again, I did not expect to see this. I thought I'd see like dipoles of temperature everywhere, because that's how I think the circulation would operate. But it really is actually acting to reduce the response to CO2. I think that's probably just as simple as meridional eddy fluxes of the poles, and something to do with the way the circulation impacts clouds in the tropics. I think that may explain that dynamical climate sensitivity and cloud connection. The responses appear more coherent and easier to understand than the total response. The RC response is to wipe out those clouds. The circulation response is to rebuild them. It's much easier to view, this figure versus this figure than rather than look at the total response. And then I think part of the reason I didn't expect this, because we usually think about climate feedbacks from a column and radiation perspective. That's, I'm sure, because the tool we use to investigate them usually is an offline, RTM. But I think it's possible that, to really understand these things, we've got to start thinking of feedbacks in all dimensions, which is hard with an RTM, but I think maybe this kind of framework where you fix things, folks have done this with cloud logging experiments, but I think if we were robust about this, we'd have a better handle on understanding all of these feedbacks. Anyway, that's all I have. Thanks.
I really like this result, even though I don't understand it. So, so what seems to happen is if you allow circulation, somehow the air system globally is more efficient in getting rid of heat. So the temperature doesn't rise as much. The question is why? You talked about low-level clouds in the subtropics, and then you mentioned V prime, T prime.
Yeah.
But V prime, T prime really, it's just a vertical component of the EP flux. It's not really a transport of heat, right?
Yeah.
Because, if you look at the conventional Eulerian-Zonal equation, most of the dy of V prime, T prime is canceled out by the T bar dy and Ws and so on, right? So you have this tremendous cancellation between zonal mean and eddy flux divergence. If you go to transform Eulerian means, these terms don't even appear.
Yeah.
Right. So that's the question. You think, I don't see how you can think of V prime T prime as having anything to do with transport of heat in a meridional direction. So I don't know if that's a mechanism, but the clouds is really interesting. If in fact they are changing in the way that you have shown here.
Yeah, we can talk more about that.
Yeah, no, this is fascinating. A really cool result.
I think there's also, just to add, and this is just bury down the heat flux path more, I think there's a bit of a, I think it's Planck feedback where, anyway, I think there's a reason why even if we go with the diffusive V prime T prime argument, why you expect that because it's resulting in changes at the pole, those tend to overwhelm the net changes that you see in the tropics. There's a temperature effect too to how these range of things shake out. Sure. Am I good on time? I don't know.
Well, we can do whatever we want.
Maybe we'll just finish with one more question. Sure.
I was wondering, so you get the eddy heat fluxes from the and V from pre-industrial, right? And you impose it in the 4 times CO2 experiment, right? Can you do the missing bit, being take your eddy fluxes and V from the 4 times CO2 experiment and impose it in the pre-industrial control?
Yes.
And then would that help you to reinforce that the processes you are seeing are actually, like the second equivalent experiment, you could presumably say yes, they are the clouds, they are the heat fluxes, and then you might be able to say something about the additivity, I guess?
Yeah, there's sort of two sides to a coin here, and one is kind of like building in an equilibrated response and one's kind of an equilibrated forcing. I can talk to you about that because we did this in an idealized model and looked at, when you force the control climate with the future changes. And I have that running right now, a pre-industrial control force to 4 times CO2 circulation.
Okay.
And broad brush, some of this stuff's consistent, but there's then some differences that I think show that it's not additive.
Okay.
So yeah, I would say additivity is probably not going to happen for this kind of stuff. But I think that's the purpose of the experiments, is trying to get a grip on the non-additive stuff that you can't address with like an offline transfer model, basically. Yeah, anyway.
I'm a fan of idealized experiments, so
Okay.
I think this is really cool.
Okay, okay, sure. Is it?
Also, have you considered the feedback from stress relief?
Yeah, that's a good question. I am repeating this red line, but with just the stratosphere fixed to the pre-industrial control, and then I'm also, I haven't done it yet, but I'm running it now. I do have a feeling that this is another good way to look at the stratosphere contribution here. Yeah. Okay. We've got time for discussion, and I don't have anything in particular prepared. This is really, we've had a lot of overrun discussion periods in this meeting the last couple days, so I wanted to open it to folks in all the working groups here. You've seen, especially folks who are not internal to NCAR. You've seen a lot of development talks too that I think have maybe some. I think we want your input to know we're going the right direction with a lot of this. I think some of you are currently working with folks to improve some aspects of the model, but I wanted to open it up to the floor, and especially anyone from outside NCAR, if they have any comments, questions, or suggestions, or want to talk or revisit anything that we've talked about the last couple days.
This is just a question about the timing of model development milestones that NCAR is thinking about right now. The workhorse model, in particular, where's the macro going, and where do you want to be? Is it maybe this summer, or are you thinking more about the next CMIP? Do you have any milestones in mind for the model development?
Yeah. And I can also pull, so I can say a few words on that, and also say a lot of our current development is really, I feel, set and timed by the development of the workforce. So I think, right now our goal was for this meeting to have the 135 level version of the model at some kind of reasonable configuration. But we really held back on that because not just the water vapor issue, there were a whole lot of things. And then when we did that, we also then discovered this topo bond SE. So I think the goal overall of CSM, and I think Dan can correct me if I'm wrong, is to really have by fall, at least for AMWG, I think to have a lot of the stuff locked in fall, spring, 2023, 2024, just to get everything scientifically locked and done for upcoming MIPS. And I feel like we are going to want to stay as close to that timeline too. So my attitude is from now until fall, we need to get WACM SE 135, 2 and 1 degree up, going at a respectable place. So at least we can have some good participation, I think. A lot of that is die core tuning right now, but it's also like getting things like TUV in. And then the difficulty too is getting this to mesh with things like, Musica and SEMA. So there's about 1 million things changing under our feet right now. But I think one goal is to make sure that we have the new configuration ready to go no matter where it plugs into. that's kind of an upcoming, that's kind of the timeline is by the end of the year, I think. It needs to be pretty.
Are you
Simone should
confused?
say something too.
Are you confused now?
I'm always confused.
Yeah, so maybe,
Welcome
I
to
mean,
the party.
I mean, there's so many things in play here. 135 level is SC, right?
Mhm.
And I mean, I presume that's what CAN 7, WACAN 7 are going to, including the workhorse model, right?
Yeah.
So the 135 is just a really high top version of that. And I suppose it's the best bet for WACAN. I don't know how WACAN will survive into the future.
yes,
Presumably in the workhorse model.
I'm gonna try to bring up the line.
And we'll see about that.
So-
Yeah.
Maybe I can outline a little bit, because we are all relying on what is happening in the workhorse model. And actually, the workhorse model goes to 80 kilometers. That's the basic first, and many people here, it's not only that it's an interest of the ChemChem group, right? The WebChem group is the one that is usually looking at the tuning of all these things, like the gravity waves, the QBO. So that's what we're seeing here. We really need that help right now, I think, to move forward. And the plan right now is that we are merging, and we have a basic version that doesn't have many changes yet, like not water wave or other things.
Mhm.
And we're running a base run. And we're looking at this, and actually, I'm setting up a baseline like a L93 level model. And I think it would be really important that from the beginning on, we all have a look at this, because we already know after the topography log fix, still we see changes in the winds. They are not perfect. But Julio is saying, okay, we cannot do a perfect tuning at this point, because the next step is that we're putting a lot of stuff suddenly into the development version. And that is happening very soon now. There's all these things that they talked about, reordering of physics, all new aerosol stuff, other physics, club physics, Puma. So once that is all in, and that should be very soon, we'll do a new run. And then we have a new run that has full chemistry, 93 levels. And I think hopefully that's the time where we all should look at this and compare and say, wait, we need to do some more tuning. And I mean, Julio cannot do this all by himself. So we all need to that would be really good if we from the beginning on help, because that will be the basis for the weapon model. And we're hoping that we don't have to do any more new tuning. So, and then the other thing is saying we'll get this all done in the next 2-3 months to have a new model run and starting looking at it. Then they want to do a freeze. And I want to rerun the whole physics to CCPP. And it is not clear.
This is tough. Trust me, I got experience.
It's not clear
This is very tough.
where we are in summer after that. But that means that we can hopefully analyze our current, the recent code changes and make some progress while they rerun the physics. So, and then I don't know how that merged together, but that's where it is right now. So to me, it's uncertain where we are in fall, but hopefully we have current developments going in, and hopefully we can work on getting the model as good as possible with that, and finding errors probably in bugs and other things. I hope that helps a little bit more.
Feel free to open discussion. I'm trying
Yeah.
to find an old email.
Go ahead.
with a timeline.
No, that definitely helps. I'm just also wondering, now that CAN is going to have to 80 kilometers, what will that mean for WACAN? What will happen with it?
Right, and that's where Nick, others can talk to, but that's where you come into the 135 level model that goes back to the old top of the model. So, but again, that will be put on top, so more layers. And I think, Nick, you have a schematic of the plans, because we discussed it before. It will be becoming more and more expensive, obviously, more and more levels. And that's where the 2-degree version will be.
Sure,
Yeah.
It's just a schematic, we're on the page. But yeah, I think the attitude is, this is probably a good evolution, because it means the rest of the community lower down is starting to see the need for more vertical resolution, a higher lid to get QBO and interactive chemistry into climate projections and other things. So I think it's not like Wacom as a science and modeling enterprise is going away. It's just that the lines between the exact configurations are blurred, which presents a conundrum now. Before it was pretty obvious. Are you going to use CAM like L32 or are you going to use Wacom? Part of our CSL proposal for the next 2 years was to really rigorously hit the 93 level version model against 135 in terms of a couple of things like geoengineering and climate forcing experiments. And the reason is we don't want to just dump on the community this spectrum of models and say, I hope you figure out which one works for you, because it's not so obvious. If you get away with a 93 level, you probably want to because it's going to be a lot cheaper. And so I think when we get a working version that's respectable, one of the things we really do want to do is focus on some community guidance, both for us internally, but also externally, to like figure out which versions of the model and what flavors are going to work. That said, like, you know, we've seen 1 degree Wacom, 2 degree Wacom with MA, TSMLT chemistry. Like, there's kind of a mess here right now. And I think what we're really trying to do also in the future is say, 1 degree TSMLT, if you really want it, this is probably shorter studies where you're really focused on variability, coupling. 2 degree MA, because you're looking at a longer study, if you're already going 2 degrees, you want an economical configuration anyway. So I think by keeping the level scheme the same, we're hoping that we stop avoiding this issue where we have 2 different QBOs, which is, the intent is that we can inherit some tuning from AMWG, as I'm finding out though, when you bump the lid up, that works for the QBO, but then not for other parts of the atmosphere. So I think the problem is, it sounded good that we're all stacking on top, but it's not as easy, I think, as we thought it would be. And like Sybil said, it's really tied to the AMWG development timeline, which is putting in, it's literally replacing seems like everything. And that's hard for me to figure out when I want to know what's changed and why. I don't know where we're going to be. So I think, yeah, we want to say end of year, but it's a little scary.
I would say that when they say it's an 80-kilometer lid, the sponge layer starts at 65 kilometers. If your science requires a proper stratospheric circulation, you're going to want to continue to run Wacom. Now, whether or not the model gets so expensive in the troposphere and all the extra physics and everything means that things like validating the 2 degree spectral element dicore version and tuning that up may be our workhorse for our community. We may not, be fully adapting the 1 degree model to go forward. So, yeah, and it's actually right now, we're actually arguing for less of an incremental jump for CMIP 7. Well, changing the dicore is massive. Updating club is big. There are a few things that are going to go in, and then essentially it's going to be relatively frozen because it's got to go into the coupled tuning phase. So at that point, we're going to be looking at that. I'm trying to get the TEM diagnostics into the ADF so that every time they do a run, we can tell them what you've done to the circulation with your tunings and that sort of thing. So that hopefully when it comes to us then running coupled with where we've added the extra layers, that it's not completely crazy. But yeah, I think while it sounds like a lot's going in, I think it's actually, we're scaling back on making a lot of changes. No, just that.
So I've heard
no changes.
2 people in the group complain about the gravity wave routine. And I was wondering, is this the time to start rewriting that so it's more functional for tuning and everything else?
Basically, I would like to touch with low bias, global bias above 70 kilometers to 110, because we would like to assimilate data, but assimilate data you need basically suppression of such kind of big biases. To my understanding, correct me if I'm wrong, and basically you think this is a gravity wave stuff, right?
Yeah, I think it's from, too much heating,
Too
from
much
the
heating.
kinetic energy to heat. But for the gravity waves, we really need to coordinate with HAO. Those people aren't here right now. Maybe they're online, but, there's been some work there and we need to coordinate with what they've done and whether it's relevant to the problems for the middle atmosphere.
No, this is paper there.
So from my
This is laid out
perspective,
by us, guess it.
inspector.
It's a timeline.
Yeah, but it is, I mean, it's in the settlement community.
Yeah.
It's just moving now.
Works,
Yeah.
but which is
I
different.
mean,
It's our best
We can,
guess.
we can
It's
talk
probably
offline,
is.
but
Yeah.
let's not have
Okay.
a private conversation.
Yeah.
Never mind. I won't go there. That's fine. I'm trusting your judgment. I mean.
No, it's, I mean, it's fine to show it, but it's our best guess. That's all it is. It's not based on something we're getting from the IPCC.
No, I know, but I think that's this is why CSM3 came up a year ago. This is why there's a goal to get something frozen by the end of basically this year. I don't think we will actually, but you know.
Couple tuning is starting in the summer.
Yeah.
Right?
So.
But I don't think physics is gonna evolve hugely. Like we're not gonna be doing wholesale switching out physics packages in the atmosphere after the summer, because I think if you start doing couple tuning to a brand new ocean,
Yeah.
you can't then start switching out physics packages too much.
Fair enough.
Yeah, so that's why I think there's a push to try and freeze model physics, and then it's down to tuning these latest changes.
Well,
Do you have specified dynamics running for spectral element model?
It's a capability.
sort of CCWG folks have been doing that.
So there is no current.
No, you can, yes, SD works with any dichord. It's now, the nudging scheme is now dichord agnostic. It's actually, so the SD concepts that folks used, that was a finite volume only type thing. The nudging scheme now, you can turn on any concept. It's a name list. You can, it's not like a build thing. It's just, it's there and ready to go. There's a wiki page for that. That's really good, actually. Yeah. Yeah, it should work with all dichords going forward. Any other topics for discussion? Anyone online?
Yeah, somebody mentioned the gravity wave parameterization and whether that should be revised. It would be great. I mean, I know what's wrong with it and what should be changed. But, you know, we have zero software engineering support, so I can do it.
Yeah, I think the hard thing is a lot of software engineering is going to the infrastructure right now. But that's needed. It's just,
Yeah, but
that means for the
if
rest-
things are continue the way they are, it will not be changed. We'll be stuck for that for the next cycle as well.
So if you're improving gravity wave schemes, they'll still be applicable.
And hopefully the community, what is it called? CCPP, whatever that stands for. Is
CCP, that's the all Soviet Union.
Is the way, will make it easier to plug in.
I'm doing my best to prove that way.
Yeah.
Good. That's true. In principle, the infrastructure should make it easier to do this kind of stuff. Yeah. Okay. Sorry for some of the tech issues today, but thanks everyone. Let's conclude the full atmospheric and climate stuff. There's a boundary layer session for the atmosphere. If you really want to go, let's have.
So not on the.
Have a good week.
Yeah.
I'm sure there's still some left over.
Hang on a second.
Yeah, I should.
I gotta go. I'll see you there.
What's next, sir?
So I have 12, 15.
Yes.
We are going to go to lunch.
No, I'm waiting for them to come apply for the early career.
What time you want to
thingy, so I'm waiting for them to get back to me, like, you know,
I come back.
do I have money, do I not have money, do like, they actually organize it. So-
Is Jagger
so I
going?
know.
Oh, they accepted the abstract and-
Yeah.
Okay, where's your office?
Yeah, there's no program, like fixed program, but
I don't remember that.
I only got an email like yesterday or something.
1:30. Not like that.
Yeah, no, like, you know what, I was like, I get used to the fact that I'm
Yeah, I mean,
like, there's administration too, that I wasn't familiar with, but no, I wanna go.
So I know there's a set of offices down here.
You can-
Side, in the basement. But I
Or
don't
it's
know.
not like,
Well, we can meet at the desk, say.
I was studying in the UK, and then I worked there. Yeah, it's been fun.
And if I don't find you, I will go find Yaga and see.
I know the name, I've never met.
Okay, so we'll see you then.
Yes.
Okay, so we go in
Okay.
I will be, yeah.
Okay. Yeah, lots of people like that guys.
I'm gonna make a quick stop.
Then-
Okay, we'll see you then. But yeah, I'll be in. Your talk is great. It's clear.
You know, like, it's my first, like,